Okay, now let's start. Michael introduces Michael. So we are today on the third day of our ISE summer school. Today we have an amazing tutorial about analyzing software using deep learning, which will also include some practical parts. And the speaker is Pradel. He's a full professor at the University of Stuttgart. He has done his PhD at ETH Zurich on program analysis, and then also worked at the well-known universities of TU Darmstadt and Berkeley in California. And besides that, he also received prestigious awards, the Ernst Steiner Dissertation Award, the Emmy Noether Grant, and also an ERC starting grant. So Michael, the floor is now yours. We look forward to your tutorial.
Cool, thank you very much for the introduction and welcome everybody. Yeah, so this will be a tutorial about analyzing software using deep learning, which is a topic deep to my heart because that's essentially what most of my research is about nowadays. And I'm really excited that I'm here to talk about this. The other Michael already gave a quick introduction about myself, so I don't want to repeat all of this. Just very briefly, I'm a professor at the University of Stuttgart. Did my PhD at ETH, then went to California to UC Berkeley to do a postdoc, then went back to Germany, where I'm originally from, and became an assistant professor at TU Darmstadt. Then wanted to get a bit more sun again and went back to California to do a sabbatical at Facebook, and now I'm back on the other side of the Atlantic again in Stuttgart in Germany. So now you know a little bit about me. I'd also like to know at least a little bit about you. So I'd like to ask you to take a little poll, which I've just shared with you in the chat. So if you click on that link, you should see a question that is asking you what your current position is. And if you could just take this poll, that would be great. Okay, see people taking it. So I think you can also see the results if you just reload the result page. You should be able to see it. All right. Yeah. So okay. So what this shows is that most of your PhD students. That's great. That's a good time to do a summer school like this, because in particular, if you're at the beginning of your PhD, you probably are looking for interesting topics to maybe do your research on, or look for ideas that inspire your own work. That's great. And we also have a few master students and a few industry practitioners. That's also wonderful. Cool. Yeah. Then let's get back to the actual topic and start with a bit of a broader motivation. So if you think about humans and humanity and why we are good at what we are typically doing, then one of the key features of humans is that we have this ability to develop tools. So our very early ancestors already had this. They were developing tools for agriculture, for example, for hunting and for many other things. And yeah, obviously we've evolved quite a bit since then, and also the tools have gotten a lot better. Now, what is true for humans is also true for software development, and in particular for software developers, because during software development, there are a lot of tools that developers are using. It's things like compilers, it's bug detection tools, it's code completion techniques that may be built into your IDE or into your editor. It's tools that help you with documenting software, and many other tools that we're using every day, basically, at least that software developers are using every day. Now, the question that I'm interested here is, how do we actually create these tools? And I'm going to first show you how this is done today and what's kind of the traditional way of creating all these developer tools, and then look into my vision of how these tools could also be created, which is at the core of this tutorial today. The way this works today is what you see here. So we have a lot of people, basically all the developers that exist on this planet, and then some experts who know a lot about program analysis are able to manually create developer tools, typically based on manually crafted rules and this creation of the tools typically takes quite a lot of time. So it's usually years of work. For example, if you do a PhD in program analysis, then you may spend a couple of years creating some nice technique that also gets implemented into a tool. And at the end, it works. That's great. But only a few experts can do this. So it's people who really know program analysis and who usually have done a PhD in this area. And because it's all based on manually crafted rules that target a specific scenario each time, these tools are also pretty limited. So for example, if you think about a bug detection tool, then typically these tools look for a few predefined kinds of bugs, some bug patterns that someone has observed to happen pretty frequently. And then the bug detection tool can basically support these predefined bug patterns, but nothing beyond that. And if you want to support another bug pattern, then again, you have to invest time and go through this manual process. So the vision that I'm working toward, and that is also at the core of this tutorial, is that instead of creating tools in this very manual way, I would like to learn them automatically from data. So there are many benefits of this. One of them is obviously that it's automatic. So you do not have to invest years of work to get these tools, but can potentially learn them in a few minutes if you have the right data available. Another big advantage is that it's not just a single person like this guy here on the left who can do this, but in principle, every developer somehow contributes to creating these tools because they are learned from data, which essentially means that every developer who contributes some code, for example, or contributes some code changes, will contribute to the creation of these tools. And so a much larger part of the population is actually part of this. And a nice other benefit is that because these tools are learned automatically and because they are learned from data, they can cover more scenarios and more cases than traditional tools may be able to cover. For example, if you think again about bug detection tools, which will also be one of the examples in this tutorial, then these tools potentially can address many more bug patterns, or maybe not even talk about bug patterns, simply because they are learned from data instead of relying on manually crafted rules. Cool, so this is kind of the big vision. By the way, I really like interactive presentations and lectures. So if you have any questions on the way, please type them into the chat, and the other Michael will relay them to me more or less immediately. So you can ask questions at any point in time. I know it's a little difficult in this virtual setting. It's a bit easier in an actual classroom, but please feel free to ask questions and just type them in and don't be shy. All right, so now after this vision, let's have a look at how we can actually do this. So the key idea is that we want to learn developer tools automatically. And one of the insights here is that there is a lot of data about software development out there that we can use to learn from. So this can be things like source code, obviously. I mean, that's probably the most used kind of data, but it can also be execution traces. So traces that tell you something about the runtime behavior of a program. It could also be documentation, because that contains a lot of interesting information that is encoded in natural language or maybe some other format, and that also tells us something about software. Or it could also be bug reports that tell us what is wrong with a piece of software and what someone wants to have changed. And these are just examples, so there are many, many other kinds of data that could be used here. And then all this data can be given to some form of machine learning, and we'll look more into this in a few minutes, which then at the end learns a predictive model or a predictive tool that then helps us achieve a specific software development task. So for example, you could have a predictive tool that learns to complete your code, or to find bugs, or to help you with documentation. And we'll see more concrete examples of this throughout this tutorial. All right, so and then once you have this predictive tool, the thing you do is you take some new code, or maybe some new execution trace, or maybe some bug report that was not looked at previously, and then this predictive tool provides whatever the developer wants to know about this new piece of data. So we learn from one set of data, and then once the model is trained, can use it for other examples, for example, other parts of code. All right, so now machine learning is this box in the middle. So in particular, what we look at in this tutorial is one class of machine learning algorithms that you've certainly all heard of, namely deep learning, which refers to neural networks and in particular kinds of neural network architectures. The deep here typically refers to the fact that there are multiple layers. We'll see in a few minutes what these layers actually are and why it's sometimes good to have more than one. In a sense, deep is also a bit of a marketing term, just because it sounds great, but yeah, most of the time it refers to multiple layers. One of the key characteristics of deep learning compared to many other machine learning algorithms is that you do not have to manually engineer and design the features and the representations of the inputs you're talking about, but these features and the representation is extracted automatically because it's also learned in a way. So for example, if you talk about source code, we do not have to explicitly say, okay, if this token is present and if that token is present, then this and this happens. But we just provide all the code, for example, all the tokens in a piece of code to a deep learning model, and then it automatically learns what features of this code is most important and how to internally represent this data. As you've probably seen, deep learning has revolutionized already a couple of other areas, speech recognition, vision, and also game playing with the AlphaGo model, for example. And the idea here is that this can also be done for software and for creating software developer tools, because deep learning is a really powerful technique. So let's see how we can apply it to software. All right, if you have any questions already at this point, again, feel free to type them in. Otherwise, I'll just keep talking. I can do this for a very long time. So here's an overview of what I want to do in this tutorial. So there are essentially 4 different parts. One is I'll start with a few basics about neural networks and deep learning, because since this is the summer school on software engineering, I assume you all know a bit about software and how to analyze it, at least some basics, but you may not know that much about deep learning. So I'll spend some time explaining some of these basics. Then we have 2 examples of learned developer tools, which we'll spend some time on each. One is this tool called Deepbugs that is essentially a bug finding tool that automatically learns how to find bugs. And then we look at Typewriter, which is a tool for predicting types in a language like Python or JavaScript, where you do not have type annotations by default. And then at the very end of the tutorial, we'll have a hands-on exercise where you'll try out a simple version of one of these 2 examples. So it's a simple version of Deepbugs by yourself in the browser, basically, and hopefully get a better idea of how this really works also on the more concrete implementation and data level.
So Michael, there is one question at this point. Jenderson asks, how far are we from the vision of AI-enabled dev tools? What are the main challenges for adoption?
Oh yeah, excellent question. So this, I mean, the reason why I call it a vision is of course because we are not completely there yet, right? But I think we are, I mean, there are really strong signs that this is able to work in practice. So as we'll see, so the 2 examples that I'll cover here in this tutorial, Deepbugs and Typewriter, are both used by practitioners now. So Deepbugs is available as a plugin for all the JetBrains IDEs, and yeah, thousands of people have already downloaded these plugins. And Typewriter is something I've worked on while I was at Facebook, and this is actually now in use at Facebook. So I think these AI-enabled developer tools are already there. This vision of really covering the entire space of development tools and clearly outperforming the traditional way of creating these tools, I think we're not yet there yet. So right now it works in particular application domains, but we're not completely there yet. And I'll talk a little bit more about the main challenges that remain at the very end of the tutorial. So I'll hold this question until then. Cool. So let's then get started with the first part of this tutorial, where we look into some basics of deep learning. So as an example that is not really about software, I'll cover here the example of handwriting recognition, which basically means you're given a simple image, like the one that you see at the bottom of the slide. And this actually, there are multiple images because we have multiple digits. And then what you want deep learning model to do is to recognize which of the digits are here in this image. So for this given image, it should probably say 5, 0, 4, 1, 9, and 2. For human, this is typically relatively easy, but it's pretty challenging for a computer. And yeah, machine learning has spent quite some time on trying to get better at this. And after many other attempts, deep learning has eventually taken over and now achieves more than 99% accuracy in identifying or recognizing digits. So let's have a look at how this really works. And to do that, I will switch to a different window. Oh, okay. So there's another question. Maybe I'll take this before going there.
I mean, the question is whether this research stream is also interested in why certain outcomes come to pass, or mainly to predict the outcomes.
Yeah, that's also a very good question. So one of the big problems of deep learning in general is explainability. So explaining to a user why a certain prediction is made. Deep learning for code or for software is not an exception to this general challenge. So this is still an open challenge, but we'll see that at least for the debugs model, the model gives you some indication why something is wrong. Well, it doesn't really tell you why it is wrong, but it gives you an alternative and says, hey, if you change your code like this, then it's not buggy anymore. And this usually helps the developer to understand why the model thinks that something is wrong. But it doesn't really give you like a long natural language explanation as you would maybe get from a human who reviews your code and then gives you comments. Okay, let me change just the window that I'm sharing for the next few minutes. So you should now be able to see this currently white window in which I'm explaining a few handwritten notes. So the first thing I would like to just explain is what is a neural network? And essentially a neural network is a network of neurons, as the name already suggests. And what this basically means is that we have some of these neurons, and we look at what these neurons are in some more detail in a minute. And these come in as the input. So our input is somehow encoded into a vector of numbers that we feed into this first layer of neurons. So this is the input layer. And then in the network itself, we have a couple of hidden layers. There are many more advanced architectures, of course, but this is just one possible way how a neural network could look like. So these are the hidden layers. And then at the end, we want to predict something. And in the most simple case, this is just one neuron. Of course, this could also be many more, depending on what exactly you want to predict. And this is then what is called the output layer. And now all of this, of course, needs to be connected in some way. And we'll see different ways of how these connections could look like. But the most simple way is that basically each neuron of one layer is connected to all of the neurons of the next layer. So basically, we would have all of these connections here like this. And then many more here. And then the same here. So basically, all from one layer are connected to all in the next layer. And then we have these three connections here, and then all the data basically flows from left to right. Getting back to this example of recognizing digits. So for example, what we could encode in this input layer are the pixels of an image. And then what we want to predict is something about the image that is given. So for example, this could be in the most simple case, a model that just predicts whether this whether the given image represents, say, the digit 5. So this would just be the probability whether this is the digit 5. So yeah, that's the basic idea of these neural networks. Now let's look into it in a little bit of more detail, and let's have a look at what actually these neurons mean. So right now they're just these little circles, but let's have a slightly more detailed look. So the most basic kind of neuron, which is actually not used in practice, is a perceptron. And the reason why I still want to explain what this is because this makes it relatively easy to understand why we actually need more than just this. So this is the most basic kind of neuron. So what is characteristic of these perceptrons is that the inputs and outputs are binary. So basically it's always just 0 or 1. And then the output is computed from the inputs based on a couple of parameters. So essentially, it looks like this. We have some number of inputs and then one output. Let's call these inputs x1, x2, and x3. And again, the inputs and outputs are both binary, so they can just be 0 or 1. And now in order to control what the output is depending on the inputs, we'll have some weights, a weight 1, a weight 2, and a weight 3. So this should be a W. And we also have a so-called bias, which is just a constant factor that is also taken into consideration to compute the output. And now given the inputs and the weights and the bias, we can compute the output of a perceptron as follows. So it can either be 0 or 1. And what we here say is that it will be 0 if the weighted sum of the inputs, so we just go through all our inputs, and for every xj we multiply it with the corresponding weight wj. And if this weighted sum is below some threshold, then we say that the output will be 0. And in all other cases, so if all of this is larger than the threshold, then we say that the output is 1. And a slightly more convenient way to write this, which is also more similar to what we use to describe neural networks, is to say that it's 0 if we just take the weights times the input plus some bias. And if all of this is smaller or equal to 0, then we say the output is 0. And if all of this is larger than 0, then we say that the output is 1. And here all these W's are the weights, and the B is the bias. All right, so this is now the most simple kind of neuron, which is so simple that it's actually not used in practice, and we'll see why. But just to check if you got this idea, let me just make an example, and then I have a little poll for you to check your understanding. So in this example, let's assume we want to encode a decision that you might make, and this is the decision whether you want to go to some kind of cheese festival. Okay, so the output that at the end we want to predict is whether you go to this cheese festival or not. It's a very relevant question in practice. I mean, you're probably asking yourself every day, should I go to a cheese festival or not? So here comes the solution. You just need to ask this perceptron. And you take this important decision based on 3 factors. One is the question whether the weather is good, because nobody likes to eat cheese when it's raining. The second input is whether your friends are going, because eating cheese together is certainly more fun than eating cheese alone. And then there's also another minor factor, and that's the question whether you actually like cheese. And now given these 3 inputs, which, because we still talk about perceptrons, are binary, so just yes or no, we want to decide the other yes or no question, do we go to the cheese festival? And in order for you to actually make this decision, we now need to set these weights and biases, and let's just assume that I'm setting them like this. So the weights are 5, 3, and 1, and let's assume that the bias is -7. And now, given some concrete inputs, so for example, a day where the weather is good, where your friends are going, but you actually don't like cheese, you can now decide whether you still want to go to the cheese festival. And this is basically what I'm asking you to do. So let's assume that x1 is 1, so the weather is good. Let's assume that x2 is 1, so your friends are going. And let's assume that x3 is 0, so you actually don't like cheese. Then now the question is, do you go to the cheese festival or not? And just to make this a little easier, let me just briefly go back to the previous slide, because I guess you want to have a quick look at this formula again. So just stay here for a few more seconds, and then you can think about this problem. All right, so I'm posting another link in the chat where, so now I'm going back to the concrete example where you are invited to now vote whether the output of this perceptron will be yes, let's go to the cheese festival, or no, let's not go, given these concrete inputs that I've shown here and given the weights and biases. All right, so I see many people voting. That's wonderful. And almost everybody says, yes, let's go to the cheese festival. And that's also the correct solution, because basically what you do is you compute this W times X, which here is 5 times 1 plus 3 times 1. Oops, sorry. Plus 0 times 1, which happens to be 8. And because 8 plus the bias, so 8 minus 7 is more than 1. So the output it would be 0 if 8 plus our bias, so minus 7 would be smaller or equal to 0, but it is 1 if this is larger than 0, and this is actually larger than 0 because it's 1. So what we here decide at the end is that we go to the cheese festival. All right, so So now given these perceptrons, you can already do a lot of interesting computations. And one example just to show you that just using this very simple kind of neuron that is so simple that people actually don't use it in practice, you can already achieve quite a bit. Let me show you an example of computing a logical function using just a perceptron. So in this case, what we want to do is we want to build a simple NAND gate, so not AND gate. And one way to do this with a perceptron is to do the following. So for a NAND gate, we want to have 2 inputs and then compute the output based on these 2 inputs. And again, we need these weights and biases. And what we want to achieve at the end is the typical decision table of a NAND gate. So let me just write it down for you quickly here. So there are 4 different cases what the inputs and outputs could be. And for a NAND, we want to have the output 1 if we have not logical AND of the 2 inputs. So basically what we'll get is this, because there's only one case where AND is true. That's when the inputs are 1 and 1, and not AND is then the inverse of this. And now the question is, how can we get this using our perceptron? And actually there are multiple ways, but one of them would be that we say W1 is -2, W2 is also -2, and the bias is 3. And now I'll let you check that this is actually correct, but you hopefully believe me and see that just using these very simple neurons, the perceptrons, you can already compute a logical function, in this case, the NAND gate. So let me just quickly move back to my other screen, my other window. Right, so what you, Are you seeing the right window now? I never really see what you're seeing. No. Zoom does strange things with me. Okay, so now.
No.
Oh, someone is saying the perceptron cannot solve the XOR problem. Let me think about that. I guess I need to think a little longer. That is no. I think you can solve every problem. At least, well, not with a sim. Okay, let me correct this. With a single perceptron, you can't probably. But what we'll see now is that using more than one of these NAND gates or NAND perceptrons, you can build more complex circuits. And from just NAND gates, as you probably know from some undergrad course, you can actually express arbitrary computations, right? So just having these NAND perceptrons allows you in principle to express any kind of computation. Yeah, okay, that statement is more precise. A single, yeah, okay, fine. So just to give you an example for a more complex computation that you can express if you combine multiple perceptrons and build them up in a way where you essentially have multiple layers. Let's have a look at a simple adder that just adds 2 bits. So on the top of this slide, you see how this would be done using the good old logical NAND gates that you've probably seen somewhere. And on the bottom, you see how you would do exactly the same. So it's basically the same kind of infrastructure using a network of perceptrons where each perceptron is configured the way I've just shown you so that it serves as a NAND gate. All right, so there's another question. Multi-layer neural networks can solve XOR, I believe. Yeah. So as I'm showing you here, so basically any computation can in principle be expressed using just NAND gates. You just need to combine enough of them, basically. So that means that also includes XOR, of course, and of course also more complex algorithms. Cool. Okay. Happy to see that you're following and asking questions. That's wonderful. Good. So then let's move on and think a little bit about this challenge that I haven't really talked about yet here, and that is how do we get these weights and biases? For the NAND gate, I've just written down the weights and biases, and magic, you actually get a NAND gate. But if you have a more complex network, then the big question is how do you actually decide on the weights and biases? So one option would be to hand tune them. You could basically go through all the weights and biases and change them through some manual process until the network actually does what you want. But obviously this isn't really feasible for more complex algorithms and more complex networks. So the other option, and this is actually what machine learning, and in particular machine learning on neural networks is about, is to learn these weights and biases automatically, given some data that allows you to basically decide which weights and biases would be good so that for the given data, the network does what you want it to do. Now, in order to make this possible, there's an important precondition that we need to talk about. And I somehow think you always see my entire screen with these 2 windows. Can someone confirm that you, yeah, I can make the slides available. Can someone confirm that you now see 2 windows?
No, we see your presentation.
Only the slides? Okay, then interesting. Yes. Then the Zoom app is lying to me, but still doing what I want, so that's good. Okay, so let me then move back to these handwritten notes. And let's talk about what is necessary in order to actually be able to learn something. So yeah, what we want to do here is making this learning, so this automatic process of finding out the best weights and biases possible. And if you think about what is always needed if you want to learn something, it's if you get a little bit of feedback, you're able to become a little better, right? So so that given enough feedback, you can basically be better and better. And the same is true here in this in this neural network scenario. So if you think about a simple model that maybe looks like this, so we have some input neurons, a hidden layer, and then an output layer. And again, let's just assume that all of this is fully connected like this. Then what you want to have is if you take these weights and you get some output, and let's say the output is not exactly what you want, but then you change the weights a little bit by adding some delta W to these weights, then what you want is that the output also just changes by a little bit so that you get delta output. So basically a small change of the weights and also the biases should cause a small change of the output. Now the problem is that the perceptrons do not really provide this property. Okay, so if you just look at these perceptrons, then they don't give you this property. And the reason is that essentially the output is a step function. So if you think about this definition of the output again, then yet another way to write this is that this is the step function of the weights times the input plus the biases, which means that it looks something like this, where the output can be either 0 or 1, and then you have this step function that basically says at some point the output immediately changes from 0 to 1. But you don't have this way of gradually improving the output based on small changes of the weights and biases, but it's more like suddenly it works, and then suddenly, of course, it also does not work again. All right, so now what can we do about this? Well, the solution is relatively easy. Instead of using this instead of using the perceptron, we'll use a slightly more complex neuron, and one of the ones that is used pretty often here is the so-called sigmoid neuron. So let's have a look at how this works. So again, we have this neuron, and again, it produces some output. And again, the output is computed based on some inputs, x1, x2, and x3. And again, as before, we'll have some weights here and also some biases that determine the output. But now the big difference here is that both the inputs and the outputs are not binary values anymore, but are arbitrary values in a given range, in this case in the range from 0 to 1. So they are in 0 to 1 and not just 0 and 1. And this is the big difference, because now if the output is not exactly what you want, you can gradually get better and make it closer or bring it closer to the output that you actually want to have. And the way this works is the following. We are basically using this sigmoid function, which I'll explain in a few seconds, and apply this function to the output of w times x plus b. And this thing here is the sigmoid function. And the way this is defined, is as follows. So take some value z, and then essentially computes 1 divided by 1 plus e to the power of minus z. And if you look at how this function looks like, then you see that it looks something like this. So my drawing skills are not perfect, but it looks roughly like this. And what you see now is that this is not a step function anymore, but actually you can have a small change in the input, so on the x-axis, and this will give you a small change on the outputs on the y-axis. And instead of having this huge jump at some point, you will be able to gradually get better and get closer to what your model is actually supposed to do. Cool. So now this sigmoid function is just one out of many different activation functions. So just to give you some more context, there are also other activation functions, for example, rectified linear unit. So if you ever come across one of these terms, it's just another function like the sigmoid function that is used in order to not just have this step function, but to have this property that a small change of the weights causes a small change of the output. All right, so one thing I haven't really talked about yet is how we tell the network in what direction to change. So we now know that it's possible to learn by adapting the weights and biases a little bit, but we still don't know how we actually tell the network how to get better. And the way this is typically done is through a so-called cost function, which is essentially a function that tells you how bad the current behavior of the model is. So this, what this is feedback that we give to the model that tells us how good or bad the output is. And the cost is higher if the model is not yet good. So what we want to do is we want to minimize this, this cost function. Just to get back to our concrete example of recognizing digits. So let's say we have this network, and again, this could be just a few hidden layers and fully connected as we've seen earlier. And let's now assume that what this network produces is the probability that the given input, which comes in here, is a 0, or that it's a 1, and so on until 9. So basically for every possible digits, we get a probability, and the higher the probability on one of these output neurons is, the more likely the network believes that the given input is actually a specific digit. Now, if what we want, let's say we have an image and we know that it shows the digit 6. So what we would like to get here is an output vector that looks like this, where for 0, 1, 2, 3, 4, wait, 0, 1, 2, 3, 4, 5, we would say that this is, oh, there's one missing. We would say that we want this probability to be 0, and then for 6, we want it to be 1, and then for 7 and 8 and 9, again, it should be 0. But now what the model actually does, given the weights and biases that we currently have, could be, for example, that it tells us that, well, okay, for 0, 1, and 2, it believes that this is certainly not the right digit, but there's a 20% chance that the output could actually be 0, 1, 2, 0, 1, 2, 3. And then maybe for 4, it's pretty certain that it's not. For 5, it's also pretty certain. For 6, it believes, yeah, okay, 70%, I think this could be a 6. But it also gives a non-zero probability, let's say, to 7, and then again 0 and 0 for 8 and 9. So as you see in this example, the actual output is not what we want it to be, but it's relatively close. Now, in order to give this model feedback about how good it is, we need to somehow compute a cost. And there are many ways of doing this. I'll just to give you an idea, give you one example here, which is the quadratic cost function, also called mean squared error, that basically looks at all the expected output vectors and all the actual output vectors, and then computes cost from the difference between these vectors. And the way this works is that we look at all the n training examples that we have. So we have some data set of not just one digit and image of a digit, but multiple. And let's say n is this number of training examples that we use to optimize these weights and biases. And then we go through each of those. And for each of these input images x, we look at the output y of x that we get from the model and subtract the, oh, sorry, we look at, yeah, and subtract from this what we actually see. So sorry, the y of x is what we want the output to be, and the a is the actual output that we get. And then we compute the difference between these two, take the L2 norm and then the power of this. And then we add all these differences up and divide it by the number of inputs we have. So basically, it's the mean of the squared error, and this is also why this is called mean squared error. Or quadratic cost function. All right, so to check if this idea is somewhat clear, I'll now have another little quiz for you. So maybe while I'm switching to this other window again, you may want to maybe copy this formula that I just wrote so that you can participate in the quiz. I'll just give you a few seconds to actually do this. And then I'm moving here. Voila, where we now have a little quiz where we have a slightly simpler problem. So let's assume there are only 3 digits, 0, 1, and 2. And we have just 2 training examples. So usually in deep learning, you have a lot more, but let's say we have just these 2 here. And for each of these training examples, we know what digit it is. This is the vector that we actually would like to get. So the first example is 1, and the second example is a 0. But our model currently, oh, sorry, I explained it the wrong way around. So the second is what we want to have. So this is the desired output. And the first is what the model actually gives us right now. Oh, no, actually, sorry, my table is wrong. So yeah, so let's just swap these 2 column headers here mentally. So what we want to have is this very clear picture where we can say that the first example is a 1, the second example is a 0, but what we actually get is slightly different because actually for the first example, the model is very unsure whether it's 0 or 1, and for the second example, it's actually correct. And now given these 2 examples with an actual and a desired vector, the question for you is what is the cost that we compute using this mean squared error cost function? And I'll again share a link with you through this chat where you are, where I'm asking you to do this computation, compute what the cost is, and then vote in this little poll for the right answer. Okay, a few people have already voted, but I give you a bit more time so that the others who have not yet voted can also give it a try. All right, so we have some more votes in. I'll just give you the solution now so that those who maybe have forgotten the formula also have a chance to understand what's going on. So I'm just switching back to my handwritten notes. All right, so yeah, the formula you're supposed to use is this one. And for this concrete example, what we'll get here is that we have 1 divided by 2 because we have 2 examples. And then here we need to add the quadratic error for each of these examples, which means we look at the first example where we were where we are wrong by 0.5 in the first dimension, and then by positive 0.5 in the second dimension, and it was correct in the third dimension. And we need to take the L2 norm of this and then square it, and the same for the second example where we'll just have zeros because actually for the second example the model was correct. Now you can look up this definition of this L2 norm just to give it to you once. If you have a vector like this, then the L2 norm is actually the square root of the all the components to the power of 2 added up. And for our concrete example, this at the end means that we have 1 divided by 2 and then 0.5 plus 0, and this happens to be 0.25, and this is also what most of you have actually voted. Cool. So let me just switch back to my slides. And let's have a look at how we can now actually minimize this cost function. So now you know how to express how bad the model is, and we know how what we want to do. So now let's have a quick look how we do this. Here I will not go into the mathematical details because this would go a bit beyond the scope of this tutorial, but I still want to give you an idea of how this works. So the goal of the actual learning is to find weights and biases that minimize the cost function that expresses what we want the model to do. And the most common approach to do this in neural networks is gradient descent. So the basic idea here is that we compute a gradient of our cost function, which is the vector of partial derivatives, so that we can, from the point where the model currently is, move closer toward the minimum of this cost function, basically step by step. And one important term here is this notion of a learning rate. So if you ever implement a neural model yourself, you probably have to set this learning rate somewhere, unless your framework does it for you. What this learning rate basically determines is how large the steps are that we take each time when we are trying to move closer to the minimum of this cost function. So just to show you a few more, or explain a few more terms that come up again and again when you talk about these neural networks. Let's now have a look at how this gradient descent is typically done in practice. So if you have a lot of training examples, then one thing you could do is basically compute the cost for all the training examples and then try to optimize across all these training examples. But this is pretty expensive. So what is typically done is that something called stochastic gradient descent is used, which basically means we take just a small sample of all the examples that we have at a time and then compute the gradient based on this small sample. So it's just an estimate of the true gradient, but it will step by step bring us closer to the actual minimum. And if you do this, then the two terms that you may want to know, one is this term of mini batches, which is basically the set of samples that we look at once in order to move along our gradient. And then there's this term of an epoch, which is the process of going through all our training examples once by going through the different mini batches in which we have divided these training examples. So what we do is we take all our training examples, split it into k mini batches, then train the network with each of these mini batches. And once we are done with this once, we say, okay, this was one epoch. And then we can decide whether we want to go for another epoch and go through all the data again, or decide that we are done. All right. Yeah. As usual, if you have any questions on this, feel free to just type them into the chat. Otherwise, I'll move on to one last bit of information on these neural network basics, which is the so-called softmax function. So this function is very often applied to the output of a neural network, because what it essentially does is it takes a vector of numbers and then turns this vector of numbers into a probability distribution. It does this basically by squashing the values that are in this vector so that the resulting numbers add up to 1, and that each of these numbers is within this typical range of probability 0 to 1. Here you see how the softmax function is defined. You do not really have to compute this yourself. Typically, of course, some implementation does it for you. So what you should maybe have a look at is this example, which shows how this works. So let's say what the network outputs is a vector that looks like this, where you could interpret larger numbers as a larger probability, just that the output of the network is not really a probability distribution yet. But then if we apply this softmax function, what we'll get is this vector, which now happens to be a probability distribution because the numbers sum up to 1 and each of the numbers is in the 0 to 1 range. Cool. So to check if this idea came across. Let's have another little quiz for which I'll share the link in the chat. So the question here is, which of these 4 vectors may be the output of a softmax function? And yeah, you should basically select the vectors that may be the output of a softmax. All right, so I see many of you voting. That's great. And most of you are saying that, yeah, the second and the third vector could be an output of a softmax function. And yay, that's correct. So the problem with the first vector is that it's all zeros. So the sum is just not 1. So this is not a probability distribution. The next 2 vectors happen to be probability distributions because the sum is 1 and all the values are between 0 and 1. And the last one, again, does not sum up to 1. So this cannot be the output of a probability distribution. All right, good. So at this point, I'll jump over a few more things I had planned simply because yeah, I was a bit slower than planned. But at this point, I'd say this is enough of neural network basics. So I hope you now have at least some understanding of how these neural networks work. In practice, they are more complex architectures that are not just about combining layers of neurons in this fully connected way that I've shown in the examples, but that are a little bit more involved. But yeah, I'll invite you to look into this by yourselves if you're interested. For now, let's now move on to applications of all of this in the space of software. All right, so as the first application, let's have a look at this tool called debugs, which is about learning to find bugs. So the very basic idea here is that we want to take a piece of code and want to train a model that is able to tell whether this piece of code is buggy or not. So essentially, what we want to have is a classifier that, given some piece of code, tells us buggy or correct. Okay. And now in order to get this kind of classifier, well, we need to, of course, train it, and we will train it using 2 sets of examples. One set of examples is code that is actually buggy, and the other set of examples is code that is correct. And then given these 2 sets of examples, the classifier or the model will become better and better at distinguishing correct code from buggy code, so that at the end, we hopefully have a classifier that is able to tell whether a new piece of code that it has not seen before is buggy or correct. Now, this is the overall idea of debugs, but of course, in practice, there are many questions related to how to actually do this. And one of these questions is how can we actually get the training data? So it's relatively easy to get many examples of correct code, at least under the assumption that most code that you find in the wild, let's say in open source projects, is actually correct. But it's not so easy to get examples of buggy code, and we see how debugs deals with this challenge. Another interesting question is how to actually represent the code. So code, as we typically look at it, is maybe a sequence of characters, or it's maybe an AST, or maybe a sequence of tokens. So there are many different representations. And the question is how to feed the code into a neural network where we actually want to have a vector of numbers and not any of these more structured representations that we typically use to look at code, for example, in a compiler. So to make this whole discussion of debugs a bit more concrete, let's have a look at the kind of bugs that debugs is actually targeting. And this is what I call name-related bug. So what you see here is a piece of code. The language doesn't really matter. Happens to be JavaScript, but it could be almost any programming language. And I'll just let you stare at this for a few seconds. And if someone could maybe try to spot what's wrong with this code, that would be good. So either just type it into the chat or open your mic and tell me. Okay, someone already typed it into the chat. Excellent, wonderful. Okay, yep, everybody's saying it. Great. Yeah, so the problem here is that the arguments are passed in an incorrect order because there's this function setPoint that takes two arguments x and y. And then we have these two local variables, xdim and ydim, and then we're passing them in an order that seems unexpected because we first pass ydim and then xdim. And the cool thing about this example is that you do not really know anything about the program this code comes from, and you do not really know what this function setPoint is doing, but just looking at the names, you can see that something is wrong. And this intuition is exactly what we also want to want the debugs model to have. Let me have a look at a second example. So here again is a piece of code. This is JavaScript, but again, the example works in this or similar way in most languages. And again, my question is, what is wrong with this code? So I again let you stare at it for a few seconds, and if someone has an idea, then please again type it into the chat. Exactly. Okay, I see correct answers. Right. So this this variable params is used in the loop body as an array or a vector, some sequential data structure. But then in the condition of the loop, it's used as if it was a number, and this obviously can't be true because it can either be just a number or a list or a vector. Cool. And again, this is a name-related bug because if you just look at the name params, then this typically means it's like a collection of multiple things, whereas the other name this is compared to, this j, typically refers to a number, like a loop variable, and comparing a collection of things to a number using a binary operator like less than is wrong in almost all cases. Cool, so now you know what kind of bugs debugs is supposed to find. Let's now have a look at how this actually works. So the input to debugs is a corpus of code, which is a lot of code written in some language. In this case, it's JavaScript, but you could implement it also for other languages, and actually other people have implemented it for other languages. And then what we do with this corpus of code is to generate training data. So the first step is to create these two kinds of examples that I mentioned earlier, correct code and buggy code. When we have these two kinds of examples, we then need to represent this code as vectors because neural networks take vectors of numbers as their input. So we'll see how we do this, but essentially we need to have a way to encode the correct code into vectors of correct code, and the same for the buggy code. And then once we have these vectors, we can train a classifier, which once it is trained, then serves to predict bugs in new code, where we basically take a new piece of code, again represented as a vector in just the same way as we do it during training, and then ask the classifier, hey, what do you think? Is this correct or is it buggy? Cool, so let's have a look into each of these green boxes in some more detail. Yeah, someone is asking, how do you extract correct code and buggy code from the corpus? Great questions. I'll get there in 2 minutes or so. So we'll go through each of these green boxes now, and I'll explain in more detail how we actually do this. So let's start with the first step, which is exactly what the question was just about. So how do we generate this training data? So as I mentioned earlier, it's not so easy to get a lot of examples of code where we know that the code is buggy and where we also maybe know why the code is buggy. So what we do here is to use relatively simple code transformations that inject artificial bugs into the code that we find in a given corpus. So we do this based on a set of transformations that each target a particular kind of bug. So for example, you've seen this swapped argument bugs. So essentially what we do in order to create examples of these swapped argument bugs is to take existing calls as we find them in the given code corpus, and then swap the arguments so that the code is very likely to be wrong. There's no guarantee here that the seeded bugs are actual bugs. So there are some commutative functions that where you can basically swap the arguments and nothing goes wrong. But in almost all cases in practice, this is not the case. But in almost all cases, if you just swap the arguments, something wrong will happen. Now, this idea can, of course, be applied to other kinds of bug patterns. So, for example, we in debugs also look at wrong binary operators, where we take a piece of code like the one that you see here that applies a binary operator to two operands and then transforms it by just selecting another random binary operator and just putting it into this piece of code. And if you just look at this transformed piece of code here on the right, then you'll probably get the feeling that comparing I and length with this modulo operator is not the right thing to do. And this is exactly what we hope the modelers also learn. Now, this idea can, of course, also be applied to many other bug patterns. Just one more example here, we can also introduce wrong binary operands. So let's say we have this shift of bits to the left by 2 in the correct code. Then what we could do is we just randomly select another operand, in this case, another variable that occurs somewhere in the same file, and just replace one of the operands with this randomly selected operand. And for example, then we would shift bits by next. And just looking at the names of these variables again, you get the feeling that this is not correct. All right, so this hopefully answers the question how we extract these correct and buggy code examples. Okay, and there are more questions coming in. All right, so one question is, do we manually decide which transformations to apply, and if so, how? No, we don't. So one of the nice insights of debugs is that if you pick the right code transformations, then you're very likely to get incorrect code. And you can basically apply it everywhere in your code base. What you need to be a little bit careful with is, for example, if you select other random operands like this next, what other operands you use. So if you would, let's say, always use foo, then this wouldn't really resemble a real bug because developers do not use foo all the time. But if you use another operand that occurs in the same file, then this is a more or less realistic bug, and then the whole idea works out. Okay, then there's another question. Can't we just find examples of buggy code for training from, say, Stack Overflow, GitHub issues, and similar places? Yep, that's a great idea. And I think this would be another way of approaching this training data generation problem. One nice property about these artificially injected bugs is that we know exactly what kind of bug we're injecting. So if we train a model so what we'll do, I haven't talked about this yet, but what we'll do is we train a model that is that looks only at examples of one kind of bug. So it's, for example, a model able to distinguish between correctly ordered and incorrectly ordered arguments. And if this model tells you that there is a bug, you don't just get this warning, hey, there's a bug, but you get a more detailed piece of information telling you there is a bug because I think you've swapped the arguments and I think you should swap them, and then it's correct. And this is, in practice, much more helpful than a model that just generally tells you that a piece of code is buggy. And if you now would get training examples from, say, GitHub issues, it's not quite clear how you would associate this kind of bug with all these examples. So I'm not saying this is not possible, but yeah, that's the reason why we went for these artificially injected bugs. Cool, okay, so that seems to answer the question. All right, so now the next part of debugs, once we have this training data, is to represent the code as vectors. And one of the key insights here is that we are exploiting the implicit information that is given in the identifiers that you have in source code. So when programmers write code, they usually use more or less meaningful identifiers because they themselves have to read the code and other people may have to read the code. So you don't just name all your variables A, B, C, D, E, but you give them more meaningful names that then convey the semantics of the code that you're writing. And the cool thing about deep learning is that it's really good at reasoning about natural language. So what we do here is we use this information. And the way we do this is by using a concept called word embeddings, which probably many of you have already heard somewhere. So the basic idea is that you have a function that takes a word and then maps this into a vector space such that similar words, or in our case, similar identifiers, will get similar vectors. So you can think of this basically as a huge space, and words that are similar or identifiers that are similar will have points in the space that are close to each other. There are many ways of computing these word embeddings. What we use here is a model called word2vec, which now is a couple of years old, and was one of the first to really popularize this idea of word embeddings in natural language processing. And we here apply it to a corpus of code and train this word2vec model on token sequences of JavaScript code. So what this gives you is illustrated here in this little plot. So what we see here is one such space of identifier names. In reality, it's a space that has many more dimensions than 2. So this is a projection into 2 dimensions, just to be able to show it on a slide. And what you see is the point in this space that different identifiers occupy. So for example, you have these 2 identifiers here, container and wrapper, that have semantically relatively similar meanings, right? The container and the wrapper is not exactly the same, but close. And they also happen to be close in this vector space. So the same is true for some of the other identifiers that we have here. So for example, this cluster of identifiers is somehow about messages and alerts and errors and things that go wrong, whereas these here are all sequential data structures. So list and LST and seek all refer to some kind of array or list or vector. Cool, so there's a question. Do you ignore keywords like if, for, else, and so on, and characters like semicolons, all these, these special operands? We do not ignore them. So when we train the word2vec model, we consider all tokens that we find in the source code, which means we also get embeddings of these special tokens, in particular keywords. And interestingly, you see things like that for and while are relatively close to each other because both refer to a loop. But then in debugs, we do not really use this information because, as I'll show on the next slide, we include different pieces of information about a piece of code, but we do not include these keywords specifically. Cool. How would variable names being treated kind of stop words? I'm not sure if I understand the question. Could you rephrase this question maybe?
So what I was trying to get is in the given code, you also have the variable names. Mm-hmm. When you try to represent them in the form of a word2vec, I mean, the way that I would declare or I would name a variable versus someone else would be different. Now,
yes.
When you're trying to do a vectorization of the code, would you go about making variable names like a stop words and remove them from your vectorization?
We could
or do some transformation.
So we could. So there are other approaches that basically do what you're suggesting. So they remove variable names and just abstract them into var1, var2, var3, or something like this. But in debugs, we specifically exploit this implicit information, and we keep the variable names as they are. And even if you use slightly different names than someone else, so let's say you call your list variable list, and someone else calls it LST or seek, then still the vector representations of these names will be close to each other because given enough data, word2vec is learning that these different names are actually referring to more or less the same concept.
Okay, thank you.
Yeah, you're welcome. Cool. So now you know how we represent individual identifiers in the code. Let's now have a look at how we represent larger code snippets as vectors. So we essentially do this by concatenating different pieces of information about a code snippet, and in particular about the names that occur in a code snippet into one long vector. And we do this in a way that is specific to the bug patterns that we have introduced in this first step where we seed these artificial bugs. So for example, if you look at swapped argument bugs, then let's say we have a statement like this, right? So this is a call with some base object. Then here we have some name of the function, and then let's say the name of the first argument and the name of the second argument. So what we do is for each of these names, we compute their embedding using this pre-trained word2vec model and take these embeddings and concatenate them as part of the vector that represents this entire call. In addition to the names, we also consider some other information. So for example, if for these arguments, we know their types. So let's say one of the arguments is a string literal, then we know that this is a string. So we also encode these types. And if we are able to resolve the function call and basically know the formal parameter names that these arguments will flow into when the function is called, then we also include these formal parameter names because they give you a pretty good hint in which order you should pass the arguments. So this is for swapped arguments. And for other kinds of statements, you can basically do the same. So for example, for the two bug patterns where we look into wrong binary operators or wrong binary operands, we do something very similar. So we look at the binary operation that is given in the code. And then for each of the operands, we again consider the name. So there will be a vector embedding here of I and a vector embedding here of length. If we know the type of these operands, we also include this. And then we also have some vector representation of the operand itself. In addition, we here also include some more contextual information where we basically look at the abstract syntax tree in which this binary operation occurs, and then look at the parent and grandparent AST node in which this operation occurs. And the reason why we found this to be useful is that an operation that, for example, happens in the loop header typically has a slightly different meaning than if an operation happens somewhere else in the code. And so by looking at the AST context, you can actually learn a little more about these statements than by just looking at the very local information like the name and the type. Cool. Okay, so now we have these vectors. Now the next step is to learn the actual bug detector. So what we are given as an input is this vector representation of a given code snippet that is constructed the way I've just shown it to you. And then now we want to predict whether this code is correct or wrong. So the output of the model should be the probability that this piece, the probability that the piece of code is buggy. And to do this, we use an actually relatively simple model here, so that the model itself is not really new. So we have this this input vector representation, then a single hidden layer of some size, and then also a little bit of dropout, and then at the end there's a vector of length 1 that just includes this probability that the code is buggy. And then during training, what we do is we have these two classes of examples, correct code and buggy code. And for the correct code, we want the model to say 0, so the probability that this code should be predicted as 0, ideally. And for the buggy examples, we want the probability to be 1. And then while training, the model is getting closer and closer to these 0 and 1 values. It will never really get exactly to 0 or 1, but very close. And it's getting better and better at distinguishing the correct code from the buggy code. Okay, so what is dropout? Yeah, great question. I haven't explained this. So dropout basically means that during training, we on purpose remove some of the information that we have in the hidden layer, for example. So you can think of this as turning off some of the neurons during training. And what this will do is it will make the model a bit more robust and help it to generalize better to other examples instead of just overfitting to the training data that we have. Yeah, I don't really have time to go into more details, but it's essentially a regularization technique to prevent overfitting by on purpose turning off a few neurons while training. There's another question. Can the abstract syntax tree of local code snippets be of use in training prediction? Definitely, yeah. And we do make some use of it, right? So as I explained here, we use this parent and grandparent AST node of a binary operation as part of our code representation. But you could think of other ways of encoding this code. So for example, there's other work that looks at recursive neural networks applied to the tree structure given by an AST. And you could do something like this to get a vector representation of a piece of code. Here we basically engineered this vector representation ourselves, but yeah, a more general approach is definitely possible. Good question. Cool. So, more questions. What is the granularity of the data points that you consider? Yeah, good question. So each data point is one of these statements. So it's either a function call like this, or a binary operation like this, or if I mean, there are also other bug patterns that you can encode in debugs, then it's the statement in which this kind of bug occurs. But it's one statement at a time, and then the prediction is whether this piece of statement, whether this statement is correct or wrong. Cool. Another question. There's probably a limit on the size of source code snippets which can be processed by a network. How do you deal with large source code files, or do you only look at snippets? Yeah, we only look at snippets in debugs, so it's one statement at a time, and that deals with this potentially infinite size, or well, a very large size of code that you might find in some files. We'll see in the second example a model where we do not do this, but look at arbitrary long functions, and we'll see how we handle that. Cool. It's good to see so many questions. Yeah, since I'm only talking to my computer here, it's great to see that there's someone listening. Good. So now we have trained this model. And now the next step is to use this trained model to predict for new code whether there actually is a bug. And what we do here is we just compute the same kind of vector representation of a given code snippet. So for example, we would go through all the calls in a piece of JavaScript code and extract for each of these calls this vector representation, then give it to the trained model, and the model will then predict the probability that this call is buggy. And because we get a probability and not just yes or no, we can actually sort the warnings that are produced that way by this probability, so that a user looks at the most likely, at the code that is most likely to be wrong first, and then works his or her way down this list until you've seen enough, basically. Cool. So yeah, let me finish this explanation of debugs. Well, actually, it's not the end, but before looking at some of the results, let's have a little quiz where I've formulated 4 sentences, and some of these sentences are actually wrong, or at least they may be wrong. And the question for you is, which of these sentences are correct? So I've just shared the link in the chat again, and I'm asking you to now have a look at these sentences and tell me whether you think these sentences are correct or not. Okay, votes are coming in. I'll give you a few more seconds to read through this and vote. All right, yeah, so most of you believe that all but the second sentence are true, and this is correct. So yes, debugs formulates bug detection as a classification problem. The buggy code examples are not extracted from incorrect real-world code bases, but instead we inject these artificial bugs. And one of the nice insights is that this actually at the end leads to a model that is able to find real bugs, even though it's trained only in artificial bugs. The word embeddings help debugs to generalize across similar identifiers. Exactly, that's why we use them. And yeah, if you want to support another bug pattern, you need to create buggy examples for this kind of bug pattern. That's also correct. Cool, good to see that. Almost all of you found the right sentences, so that's a good sign. Now let's have a quick look at some of the results. So we've evaluated debugs by running it on 68 million lines of JavaScript code, so pretty large code corpus, where we use 100,000 files, so roughly 2/3 of the code for training and the remaining files for validation. So what you see here is the number of examples that we get from this code base for each of the 3 bug patterns that I've mentioned. So what you see is that we have millions of different examples. So for example, for swapped arguments, we have 1.4 million calls that we use during training, and for the binary operations, we have even more. There's a question, I'll get back to this once I'm done with the results. Now, given this data, we train this classifier, and one thing you can measure is the accuracy on the validation data. So not the data that is used for training, but the other data that we keep for validation. And what you see here is for each of these bug patterns, how accurate the trained model is. So what you see is that the accuracy is 90% roughly, or even more, up to almost 95%. So in after training, the model is actually pretty good at telling whether a piece of code looks correct or looks buggy. To illustrate some of the bugs that you can find this way, let me just show you a couple of bugs that Debugs has detected in real software. And again, we can play this game from earlier. So I show you the code, and if someone believes to see why this code is wrong, then please type it into the chat to let me know what's wrong here. Okay, seems no one dares to guess what's wrong here. So maybe let me then tell you the solution. So yeah, you need to know a little bit about JavaScript in order to tell what's wrong here. So in JavaScript, there's this built-in function setTimeout, which expects two arguments, a function and a delay in milliseconds after which to call this function. And what the AngularJS developers have done here is to accidentally swap these two arguments by having fn, which probably refers to a function, as the second argument, but it should be the first argument. Here's a second example, and this one is it's not really JavaScript specific, so I'll give you a few moments to have a look at this, and if someone has an idea what's wrong here, then please type it into the chat. Right, exactly. So someone wrote a correct solution. So what the developer tried to do here is to basically alternate between true and false in the different iterations of this loop by just taking the loop variable I, and if you do modulo 2 and check if this is 0, you should get this alternating flag. But instead, by accident, this modulo operation is the wrong way around. And therefore, this code is just not doing what it was supposed to do. And Debugs found this because it basically sees that, well, if there's something called I and a number in a modulo operation, then probably I should be first and the number should be second. Now, beyond examples, of course, you also want to, for every bug detection tool, evaluate the precision of these bug detectors. So what we did here is to manually inspect 150 of the warnings. 50 from each of these bug patterns, and then manually classify them into 3 classes, either bugs, so that's the first column, so things that are clearly wrong and where the developers should change something, code quality issues where something is, where nothing is really wrong, but if you keep it this way, there's a pretty good chance that something will be wrong at some point, or maybe there's poor performance and you should change things to get better performance, and then false positive, so where the model is just plain wrong and doesn't really help the developer. And what you see here is that most of the bugs are actually true positives. So overall, it's 86%, which is a pretty good result and is even high compared to manually created bug detectors, despite the fact that we did not tune any heuristics in debugs. So it's all learned and no one had to really manually filter the warnings based on some heuristics. All right, so there were a couple of questions. Let me try to answer those now. So one question was, can debugs tell what the correct version of code is? That depends a bit on the bug pattern. So for some of the bug patterns, like swapped arguments, it's easily possible, because if you say the arguments are in the wrong order, then the correct order is just swap them again. And for other bug patterns, it's not that easy. So if we tell you that this binary operator looks wrong, then you still don't know what the right one is. But what you can do is essentially try to fix it. If there's a limited space of possible fixes, for example, picking another binary operator, you can try these different fixes and ask the model each time, hey, what do you think? Is this correct or wrong? Is this correct or wrong? And then you, at the end, could, for example, suggest the code that is most likely to be correct as a possible fix. We haven't done this, but that's something you could relatively easily do based on the already trained model. Then there was another question: what's the application in practice? At what point is a developer notified? That depends how you really use this. So this was a research prototype, but independently of my implementation of this, people at JetBrains, the IDE company, have written a debug slide bug detector, and this is now shipped as an IDE plugin where you basically get warnings while you type code. So if you type some code and based on the names and some other information it looks wrong, it'll give you a warning right at this point. Yeah, okay, someone else asked something similar. Is the goal of debugs to provide real-time bug detection or find these hidden bugs that human developers may not be able to see? It depends how exactly you use it. So the way the model is trained, we do not really fix one of these two goals, but you could use it either way. So what we've done for the evaluation is apply debugs to code that is already used in production. So it's more likely to find these bugs that for whatever reason people just have missed so far. But if you actually have it as part of your IDE, or maybe apply it as part of the code reviewing system so that every committed piece of code is checked, then of course you can find these bugs much earlier. And that's probably better, because if you find bugs earlier, it's always better. Okay, then someone asks, comparing this with more traditional bug finding tools such as find bugs, how many bug patterns can be supported by debugs and the other way around? That's a great question. So most of the existing bug finding tools are based on a set of patterns, and they typically have hundreds of patterns. At least find bugs has hundreds. What debugs currently supports is the 3 patterns I've mentioned here, plus 2 or 3 more. It's relatively easy to introduce new patterns, but you still have to do this. So one piece of future work that would be really interesting to look at is how to automatically extract these patterns, for example, from existing code changes that we see at GitHub. What we have done is a direct comparison to an existing bug finding tool for JavaScript, because debugs is implemented for JavaScript. So we compared against a popular JavaScript linter, and found and then checked how many of the bugs that debugs finds are found by the linter and vice versa. And what we found there is that they are largely complementary. So the linters find some bugs, debugs find some other bugs. The overlap is really, really small. I think it was like 2 or 3 bugs only. And the reason is that debugs looks at kinds of bugs that are really hard to find for traditional analysis, because traditional analysis, the first thing every traditional analysis does is to throw away the identifier names. But this is exactly what debugs is using here. Okay, then there's another question regarding model architecture. How did you build up the used network? How did you decide how many layers are appropriate for debugs? Yeah, great question. As you've seen, the architecture is relatively simple. So there are way more sophisticated models that people have proposed, and there actually is follow-up work by others that try to improve debugs by using more sophisticated architectures. And typically what happens is that the results are getting a bit better. So if you use a more clever architecture that maybe looks at more context, then the accuracy will get a little higher. So there definitely is room for improvement, and I'm not claiming that this is in any way the best possible architecture for this problem. For the question of how many layers, so what I've done here is what most people do in machine learning. I've just tried a few options, basically. I tried with 1 layer, 2 layers, 3 layers, and then after a bit of experimentation, took the hyperparameter that worked best. But again, no guarantee that this is really the optimum. Then there's a question, is debugs able to extract novel bug patterns? No, not at this point. So we rely on existing bug patterns and transformations for them to introduce these negative or buggy examples. It would be interesting to infer these bug patterns, and some people are looking into this, but so far we haven't done that. Okay, then a moonshot view question. Do you foresee compilers to not have syntax validation when neural networks are becoming more robust and become part of the IDE? So I guess the higher level question here is, what tasks should we address in a learning-based way, and what tasks do we leave to more traditional approaches like syntax checking in a compiler. I think we should not aim at completely removing compilers or traditional analyses, because they are good at some things, and we should just use them for that. But try to complement them, and sometimes also replace them through learning-based approaches. But I don't want to throw away all the existing program analysis and compiler work, because it's doing a good job. And for example, checking whether a piece of code is syntactically correct is something that a compiler is really good at, because you know the grammar of your language and there are well-known algorithms for doing that. So there's no good reason to learn a model to do this instead. Okay, and then final question for now: how many languages does it support? Does it have more or less the same precision for all languages? That's a good question. So what we have implemented is for JavaScript. What the JetBrains guys have implemented is for JavaScript and Python, but I haven't seen any direct comparison in terms of results of these languages. So I do not really know how the precision compares across languages. Good, so let me just summarize this part of the tutorial. So this was about debugs, which formulates bug detection as a learning problem. And the key idea is to have a name-based bug detector that exploits all this natural language information to detect bugs that traditional analyses are not really considering. And one of the nice insights is that even though we learn from these artificially seeded bugs, we at the end are able to find real bugs. There's a paper about this. You can also play around with the code, and actually in the last part of the tutorial, you will play with a simpler version of debugs to get a better understanding of this. All right, so yeah, let's now have the coffee break. We went a few minutes over. I hope that's fine, because
thank you very much. I think it was great, a great interaction, great easygoing tutorial on an advanced topic. So thanks a lot. Do you want to have 20 minutes break or 30 minutes break?
I would suggest to resume after 20 minutes or 21.
Okay.
So basically at half.
So we stay on schedule and start again in 20 minutes at 10:30. Thank you.
Cool, thanks. All right, so let's continue. I hope everybody had a good break. Yeah, so what we've done so far is we looked into some of the neural network basics. Now we've looked at one example of using neural networks for one particular problem in software development, and that was debugs for bug finding. And what we'll do now is to look at another application where it's about predicting types in a language that does not have type annotations by default. And this is based on a tool called Typewriter. So yeah, as we've done it so far, keep asking questions, and I'll be happy to ask any questions throughout the talk. Maybe to give a bit of context, so why do we care about this problem of type prediction? The reason is that there are these dynamically typed languages like Python and JavaScript and many others that have become extremely popular in the last few years or maybe even decade, but they do not have type annotations, at least not by default. And this leads to a couple of problems. For example, and that's the most obvious one, it leads to type errors because, yeah, you may have a type error and you just don't see it. But it also has other implications. For example, it may be pretty hard to understand some APIs because the API definition doesn't really tell you what kind of arguments a function expects and what kind of return value it will produce. And it also hampers IDE support quite a bit because if the IDE does not know the types of variables and functions and so on, things like autocompletion or jumping to the function definition just work less well. Now, fortunately, there is a technology called gradual types, which is wonderful because it essentially allows you to gradually add some types to the code base written in these dynamically typed languages, and then does type checking with all the types that are annotated, but ignores all the others. So this is great, but there remains this one big problem, and this is that actually annotating these types, in particular, if you have an existing code base that is written without type annotations, is pretty painful, and most developers do not really like to do this simply because it takes time and may not be super interesting to do. So as a concrete example, let's have a look at a piece of Python code. So this work that I'm presenting here has been done in the context of Python, but it's based on an earlier prototype in the context of JavaScript. So yeah, I think most of what I'm saying here basically applies to any of these dynamically typed languages. So in this example, we have two functions. There's one function find match, which is given a color and then returns a color or maybe none. And we have this other function get colors that yeah, just returns a list of colors. Now, what we would like to have in this Python code are these type annotations that basically tell us the types of all the arguments and the return types of all the functions, so that we can then type check this code and yeah, validate whether the code really is type correct. So just going back and forth. So this is the code without the types. And then what we would like to add is the annotations for the arguments and for the return values. You can also add type annotations in the function bodies, but that's something we do not really look at here because in practice, it seems developers mostly care about type annotations on the function level. Now the question is, how can we add these type annotations? And there are at least three possible answers. Option one is static type inference. So you can take a conservative static analysis that infers some of the types from, for example, constants that appear somewhere in the code. And usually these static type inference techniques guarantee type correctness. So whenever they tell you that there is a type, then they are really sure that this is the right type. And if you add this type, the program will still be type correct. This is great, but in practice, very limited. So as we'll see also in the empirical evaluation, yeah, many types cannot be inferred this way simply because the languages we're talking about here are highly dynamic. So there are many things that a conservative static analysis just can't reason about. Option two is dynamic type inference. So if you can run the code, and a lot of code is run somewhere, right? That's why you write it. Then you can look at the types that variables and functions have at runtime and can just use these types and annotate them. That also works well to some extent, but obviously depends on input. So you somehow need to make your programs run and be able to observe the execution at the same time. And it also misses quite a lot of types, for example, if code is not covered. Another problem is that the types you see at runtime may be more specific than the types that you actually want to annotate. So for example, if a variable can be either a string or none, then maybe you see at runtime string and add this annotation, but then you forget the fact that the variable may also have the value none, which means no value at all. And then the third option, and this is what we're looking at here, is probabilistic type prediction, where you have some kind of model that is, for example, learned from existing type annotations in the code base, and then it probabilistically predicts the remaining types in this or another code base. So option 3 is what we're interested here, and specifically, I'll show you one instantiation of this idea of probabilistic type prediction in a tool called Typewriter. So on a very high level, Typewriter consists of 2 big components. So given a program, the first component is a probabilistic type prediction technique, which is a neural model that is trained on existing type annotations, and that for one missing type annotation is predicting a type vector, which is basically a probability distribution over the types that this variable may have. And then this distribution tells you what is the most likely type, the second most likely type, and so on for a particular variable or maybe for a particular parameter or return type. And then the second part of Typewriter takes this type vector, this probability distribution, and searches for consistent types within the most likely types as predicted by the model. And the reason why we do this will become clear throughout the talk, but essentially the one reason is, or the main reason is that the topmost prediction of a probabilistic type predictor may not be correct. And if you just add this topmost prediction for each place in your code where a type is missing, you are unlikely to get a type correct program at the end. So you somehow need to find the types that at the end give you a consistently typed program, and we'll see how we get there. So each of these big steps is composed of smaller components. So for the probabilistic type prediction, we'll see a combination of a very lightweight static analysis that essentially extracts information from code, which will then feed into a neural type prediction model. And for the second component, the search for consistent types, we'll see how we make use of a static gradual type checker that can tell us whether a given piece of code with some type annotations added is type correct. And we'll use this type checker as an oracle in a feedback directed search to find consistent types, hopefully for the entire program. And then at the end, what we get is the same program as the one that's given as the input, but now with added type annotations. All right, so now let's go through these individual parts of the approach in some more detail. And as usual, if you have questions, feel free to just type them in. So let's start with this first component here, the one that probabilistically predicts types. And let's have a look at what kind of information we are actually extracting. So what I've already shown here on the slides, but didn't mention really, is that we are extracting 2 kinds of information again. So similar to what we do in debugs, we consider both natural language and programming language information. And here you can see what kind of information exactly we are extracting. So on the natural language information side, we again use this insight that identifier names convey a lot of insights about what a variable or a parameter or a function is actually supposed to mean. So we are extracting the names of functions and the names of arguments. And we also use another kind of natural language information, namely function level comments. So in Python and also in most other languages, you have some way of annotating a function with a function level comment. So these are the doc strings in Python. And we are using these function level comments because they often describe in natural language what this function is really doing. And this gives you some idea about the types that the function parameters and the return type will have. So this was the natural language side. We also extract programming language information. In particular, whenever we want to type a specific code element, say a parameter of a function, then we look at all occurrences of this to be typed code element in the code. So for example, we look at all occurrences of this parameter in the body of a function. And another piece of information that turns out to be pretty useful is to look at types that are made available in the current file through some kind of import. So in Python, you have to explicitly import types, except for the built-in types like string and int. And the fact that the developer is importing a particular type gives us a pretty strong hint that this is a type that may be useful somewhere in this file. Because, for example, the developer is calling the constructor of a class, and then maybe we need to use this class name somewhere as a type annotation. So we are, for each file that is analyzed, also extracting the set of types that are imported, and we provide this to the neural type predictor. Now, one question, given all this information, is what kind of model to use. So what you've seen is that different kinds of information. There's natural language information, programming language information, and in each of these categories, there are, again, kind of subsets of pieces of information. And what we've done in debugs, which was to simply concatenate all this information, doesn't really work because you would get a very long sequence, and also naturally, this isn't really a sequence, right? So it's different pieces of information that have nothing to do with each other. So just concatenating this into a very long, arbitrarily ordered sequence doesn't really make a lot of sense. Also, what we see is that these different pieces of information may have different structure. So, for example, for the occurrences of the to-be typed program element, we can look at this, for example, as a sequence of tokens, but this may be a slightly different structure than some of the other pieces of information that we are using here. So now the kind of model that we use is what is called a hierarchical neural network. So essentially, such a hierarchical neural network is a neural model that is composed of different submodels, and these submodels are aligned into some kind of hierarchy. So you can, for example, think of this as a tree where your input arrives at the leaves of this tree, and then you're repeatedly summarizing these different kinds of inputs into this in this hierarchy, so that at the end you propagate all the information from the leaves to the root of your tree, and then given this root, you have a summary of all the input, and can then make your prediction based on the summarized information at the root. So now the question is, what are these submodels? And the general idea of a hierarchical neural network is that each of these submodels encodes some specific part of the input that we are given. So, for example, in this type prediction context, you would, for example, have a submodel for some piece of natural language information and a different submodel for a piece of programming language information. One cool property of these hierarchical neural networks is that you can have different submodels for the different, that you can use different kinds of neural networks for the different submodels. So you do not have to have the same kind of model for all kinds of input, but you may be able to encode some input in with some kind of neural network and another part of the input with another kind of neural network, and then at the end summarize everything into a single vector. So for example, you could use for some input a feed-forward neural network. So this very simple one that I've already shown you in the first part of this tutorial. And for some other part of the input, you may want to use an RNN, a recurrent neural network, which is a kind of neural architecture that is pretty well suited for sequences of data. All right. Yeah, if you have any questions so far, again, feel free to type them into the chat. Oh yeah, here's one. Right, so you're asking what do we do with docstrings, so these function level comments where we have something like a type annotation that is already in the comment. And I think in my example I actually had something like this, right? So in my example I was showing a docstring where there is in some formalism that isn't really fully specified, a semi-formal description saying that, oh, this argument called color is of type string. That's a great question. So the model is looking at these docstrings. So it tries to learn from this information. Now, because these are docstrings and there's not the one way of writing types into docstrings, we are not sure exactly what the format is in which these types are given. So all so basically what the model tries to do here is to guess what piece of information here is actually a type. and then uses this guess for the prediction.
Yeah, thanks for the reply. I think there is a specific format though. So it's like you can I don't know, like maybe it's just some IDs that define this format, but I think there might be a lot of code where you have this like defined structure. So it might be quite easy for the model to learn it. And
exactly, yeah, that's also why we give this information. As far as I know, there's so the way you annotate the types in the code is specified by the Python language. But the way you can specify types in the comments is not specified by the language. There are different recommendations how to do this, and some projects follow the same guidelines basically. So they use the same format, but it's not really, there's not the one way of writing these types in the comments. So that's why we decided to not extract them explicitly, but to let the model learn this format, because there's not just one format.
All right, thanks.
Okay, yeah, someone else is confirming that there are different patterns of writing these types in doc strings. Cool. So, okay, another question. All right, so yeah, so the question is, it's hard to decide which network is correct or which neural architecture is maybe the best. And can I give any hint or literature link which kind of model best fits to which problem? So, I mean, there's no single correct answer here, but one way of reasoning about this is to look at what structure your information naturally has. And if it is just a small piece of information, then a feed-forward neural network is good. If it is a sequence of information, then you typically want to use a recurrent neural network. If you think a graph is a really good way to represent this, then they're graph-based neural networks. And if it's a hierarchy, you may use one of these hierarchical neural networks. So, and then there are also a couple of others. There are also convolutional neural networks and so on. So I can't really give a very extensive answer here, but yeah, if you're really interested, I actually have a longer version of this tutorial as a lecture. That is also online and available on YouTube. So if you basically want to get an extended version of all of this, where I discuss different kinds of architectures and when to use them and how to apply them to software in more detail, then you may want to have a look at this lecture. Cool. Good. So yeah, so we were here. So I was talking about these hierarchical neural networks that are composed of different submodels. And what I would like to do now is to just give you tell you about the model that we are using in typewriter, which happens to be one of these hierarchical neural networks. So let me just switch to my handwritten notes again. So we have this hierarchical neural network that we want to use for type prediction. And as I mentioned, there are different kinds of inputs that we are considering here. So one kind of input are code tokens, which we extract from different occurrences of the code element that we want to type. So we have basically occurrences of the parameters, and we also look at return statements because they tell us something about the return type of a function. Then we also look at identifiers, so specifically at the name of the function and the parameter names that should be typed. Then we also have these comments or doc strings that we are using here. And then we have this, these available types that are made available through some import, which also are useful at least sometimes. So they are not always, so the fact that a type is not yet imported does not mean that this is not the correct type, simply because by adding the type annotation, a developer might also want to add the import, but still sometimes this is pretty useful. So now let's have a look at how we use all this information in this hierarchical neural net. And what we do at first is to embed some of this information into a vector space using a similar idea as in debugs, where we want to have this word embedding that is specifically trained for the kind of information we have here, so that we get a vector representation of this information. And we do this in two ways. So one is a pre-trained token embedding. So this is again a word2vec model and other embeddings that exist nowadays might also work, that we pre-train on token sequences of Python code. And we use this to encode both the code tokens and also the identifier names, and then basically get vector representations of each code token and of each identifier. For the comments, we also do something similar, but here we use a different embedding, which is not a token embedding, but a word embedding. And so that basically means it's the same kind of model. So it's again word to vec, but now trained on sequences of natural language words and maybe some other information that we happen to see in comments. So what we do here is we take all the comments we found in a huge code base and then train this word to vec embedding based on the comments. And this will give us one vector representation for every word that occurs somewhere in a comment. Now, having these embedded tokens and identifiers and words and comments, we need to somehow summarize them further. And to do this, we use multiple recurrent neural networks. So I don't really have time to explain in detail how these recurrent neural networks work, but essentially what they take as an input is always a sequence. So for example, here, this will be a sequence of tokens. And specifically, this is the sequence of tokens that are well, around the occurrences of a parameter and the sequence of tokens in return statements. And we feed all these sequences into a recurrent neural network. And then what this neural network does is to summarize all of this into one vector that is just a fixed size vector. So even if the sequences may have different length, but at the end we have a fixed size summary of the tokens that we are given here. And so this is what we do with the code tokens. For the identifiers, we do something very similar. So we have another recurrent neural network, so that it's a different model that has different weights and biases, but uses the same architecture. And again, we get a fixed size vector that summarizes all the information that is encoded in identifiers associated with a function. And then for the comments that may be associated with a function, we again do something very similar. So we have another RNN that again summarizes all the comment information into a single vector. So the nice thing about this hierarchical architecture is that you could replace each of these components. So if you want to replace, say, the comment RNN with a convolutional neural network, which may work better, you could just do this. You just replace this RNN here with a CNN, a convolutional neural net, and then maybe it works better. So you can basically play with different variants relatively easily. And then this last piece of information, the available types, there's no need to really embed it in any way. So what we just do is to represent this as one long vector where we have all the possible types in our code base. Actually, we just focus on the top 1000. And then this vector represents with zeros and ones whether a particular type is actually available in the given file or not. So now when we have these 4 vectors, the next step is to combine them in some way. And here we take the approach of just concatenating them. So we have this concatenation operator that gives us one long vector that summarizes basically everything we know about this given function. And then we give this into a feed-forward neural network, which, for example, has 2 layers. And then at the end, what we want to get is this type vector. So this here will be a feed-forward network plus the softmax function that you've seen earlier. And the result of this softmax function is that what we get here is this type vector, which is a probability distribution over the possible types that the return type or the parameter type of a function might be. All right, so we had one question in the chat in the meantime. What are the main challenges on building these composite models? If something goes wrong in the output, it might be tricky to spot which model is not behaving as expected, right? That's indeed a challenge. That's a very good point. So yeah, because you're building a more complex model, it may be difficult to spot which part of your model is not doing what it's supposed to do. One thing you can do is to turn some of these parts of the network on and off. So in the typewriter paper, we do an ablation study where we essentially turn individual parts on and off and then see how this changes the overall result. And that gives you some indication if each of these components actually contributes to the overall accuracy that you get, or whether it's basically useless. Another thing one can do is to look at these summary vectors. So for example, you could have a look at this token this summary vector that summarizes the comment, and consider this as an embedding, and then look at the space described by this vector, and then look at individual comments in the space and see if comments that are semantically similar are actually close to each other. And if they are, then this summarization actually works. If they are not, then it probably doesn't work very well. Okay, then there's another question. Can the model predict user-defined project-specific types? Yes, it can. So what we do here is that this type vector has size 1000. And we just take the 1000 most common types that we found in Python. So this includes very high up in this list, in the top 10 or so, all the built-in types like int and string and list and dict. And then further down, you have a lot of user-defined and project-specific types that correspond to specific libraries. Now, of course, if you train this model and then want to apply it to a completely different code base that is using completely different libraries and has different project-specific types, then this will not work very well. So you basically need some training data that includes some type annotations in the libraries and in frameworks and so on that you are using. Yeah, then there was another question. I'm wondering, do you make sure all inputs contributes to the output? For example, the comments. Yeah, so we did this ablation study where we validated that each of these inputs actually contributes something on average. Of course, for a given function, there's no guarantee, right? So there may be a function that has a completely useless comment, or maybe no comment at all. And in this case, we can't guarantee that this really contributes to the prediction. But on average, at least we've seen experimentally that each of these components does contribute. Oh, thanks for the reply. Yep, you're welcome. Cool. Good. So if there are no more questions on this, let me switch back to my slides. All right. Yeah. So what we get out of this model as the prediction is this type vector, and what this type vector is, as I said, doing, it's a probability distribution over the 1000 most common types. And the model is essentially a multi-class classification model that tells us how likely each of these types is. So what we do during training to make the model learn to make this prediction is to set all types to 0, except for the one type that we know to be correct. So we train this with partially annotated code. And for each existing annotation, we have one data point where we set all types to 0, except for the type that we see as the one that developers have chosen. And then once the model is trained during prediction, what we do is we look at this predicted type vector and interpret it as a probability distribution over the types. So we know what is the most likely type, the second most likely type, and so on. Now, one question you might have about this model is how to actually train it. So there are basically two options for training such a hierarchical neural network. Option one is to train each submodel separately. So basically each of these boxes, the embedding, the RNN, and the other RNN would be trained separately, which is maybe good because then the training can focus on just this specific model and its input. And you can also ensure that this submodel is really doing what it should do. But one big disadvantage is that you then need training data for each of these individual submodels. And if you do not have training data for how to summarize a comment, for example, you have a problem. And also these submodels, if you do it this way, are not really aware of the overall task you want to do. So the way you summarize a comment for type prediction may be different than if you want to, say, generate or synthesize code from a given comment. And if this submodel is just trained on its specific piece of data, then it doesn't really know what the overall task is. The other option, and this is what we mostly do in typewriter, is to train the entire model jointly, which means we have one cost function over this entire hierarchical neural net, and then all the weights and biases in this model are optimized together, so jointly. This means we only need training data for the overall task. So in our case, we only need existing type annotations, but no information for how to summarize a comment, for example. And it means that each of these submodels is optimized for this task that we want to achieve. One potential problem is that the feedback that you get from the final prediction may get lost when you during training. So training works based on backpropagation, something that I haven't really covered here. But there's the so-called vanishing gradient problem. That means that some of this feedback may not actually arrive at one of the submodels. But if you tune these models correctly, then this typically is not a problem. So there's a question here. Can we better leverage the available type hints rather than aggregating them with the 3 RNNs output? Not sure what you mean by better leverage. So there may be better ways than just concatenating these vectors. I guess this may be what you're asking about here. Yeah, not sure what these better ways might be. Yeah, go ahead.
So I mean, maybe we can leverage the available type hints in the training stage. I mean, rather than having a vector of, for example, 1000, maybe we can involve them in the training stage. I don't know, using some kind of sub model for available type hints. I know it's just something out of my head. I mean,
So when you say available type hints, do you mean these the types that are imported in the file?
Yes, exactly. The types that we.
Okay, yeah. So one thing we have tried, and that has not worked as good as what we now do, is to use these imported types as a hard constraint. So basically, we take the probability distribution that the model predicts, and then apply these available types as a mask, sort of, that rejects all predictions that are about types that are not imported anyway. And the reason why this did not work so well is because sometimes developers have not yet imported a type, but still would want to import this type to add a type annotation. Not sure if this answers your question, but
yes, okay. Thank you so much.
Cool. All right, so so now you know how the model looks like. Let's now have a look at how we train this model. So we train this model based on existing type annotations using a multi-million line Python code base. So this was actually trained on all the Python code that Facebook has, which is a lot. I can't really tell you how much exactly, but it's a lot of code. And in this type base, there are already some type annotations, basically because developers have put this effort into adding these types. So depending on what parts of the code and what kind of annotation we talk about, it's between 20 to 50% of the code that is already annotated. And we use this as training data to then get a model to hopefully annotate many of the still missing type annotations. There was another question on the model. What if you change the RNN to GRU or LSTM? Would the vanishing gradient problem be resolved? So what we are using is actually an LSTM. So recurrent neural networks are typically either based on GRUs or LSTMs. We've tried both. They work more or less the same. So we picked LSTMs at the end, but it's not a. Or maybe did we pick GRUs? Okay, I don't remember exactly which of the two we used, but they work more or less the same. That's also why I forgot which one we used. This didn't really influence the vanishing gradient problem. So in practice, we did not run into this vanishing gradient problem. I just know that in theory this might happen. All right, so getting back to these predictions. So once we have trained the model, let's have a look at the code example that we've already seen earlier. And let's have a look at what this model would predict here. So basically, for every place where we have a type missing, it would give you a ranked list of types that it believes are the most likely. So for this color parameter, for example, it would say, well, I think it's an int, and if it's not an int, it may be a string, and if it's not a string, it may be a bool. And similarly, for this return type, we have some types that are predicted, and also for the return type of this getColors function, we have some types here. And now the question is, what do we do with these predictions? So the naive approach would be just take the topmost prediction everywhere and suggest this to the developer, because after all, that's what the model thinks is most likely. Yeah, this doesn't really work that well in practice, and we'll see why. So there are basically two challenges here. One, and that's the reason why we can't just take the topmost prediction all the time, is imprecision. So some of these predictions are wrong. It's just a probabilistic model. It's not perfect, so it will be wrong sometimes. And if we do not do anything about this, then basically we say the developer must decide which of these suggestions to follow, which is still quite a bit of work, because then for every place where you have a missing type, a developer must look and say, oh yeah, I think this is correct. I think this is correct. Oh, this is not correct. The other problem, and this is a problem that comes up when you try to reason about which of these predicted types to actually use, is that you have a combinatorial explosion of possible options. So for each missing type, for each place in the code where a type could be annotated, there is one or typically more than one suggestion. And now if you say we do not take the topmost all the time, then you maybe want to take the second here, the first here, the third here, and the first here again. But exploring all these possible combinations gives you this combinatorial explosion. And in practice, it's just not possible to try out all these combinations if you have a larger file or a larger code base. And these two challenges are basically motivating this second step of typewriter, where we now take this type vector that is predicted for each missing type annotation, and then have a search that tries to find consistent types in these predicted types, and validates the type annotations using a static type checker. So let's have a look at how this works. So yeah, what we have is these top K predictions for each missing types. And then we use one of these gradual type checkers to basically filter them. So for all of these popular dynamically typed languages that allow for optional type annotations, there are at least one or typically more than one of these gradual type checkers. So for Python, for example, you have Pya and MyPy. For JavaScript, there's Flow. And what they all do is they take a piece of code with some type annotations and then tell you whether this piece of code is type correct given the available annotations. But now if you have, say, S of these type slots, and for each of these S type slots, you have K predictions, then the number of possible type assignments, so basically ways of adding types to a particular type slot, is K plus 1 to the power of the size of S. And in practice, this is just too large to explore exhaustively, simply because we have a lot of type slots in a realistically large Python file. And even if you just consider, let's say, the top 3 predictions, you still get a lot of possible type assignments, and type checking each of them for every file is just not feasible in practice. So what we do instead is to use the type checker as a way of providing us feedback. So we formulate this feedback function that basically returns a score where a lower score is better. And so the goal of this whole search is to minimize the feedback score that we get from the type checker. So what we consider here is two things. We consider this n missing, which is the number of type annotations that are missing. So we want to have as few as possible of those, because we want to basically assign a type to as many of the missing types as possible. And then the other factor here is the number of type errors that we get. So for every type error that we get, something is wrong. So we want to minimize this number of type errors. And then V and W are just some weights that allow us to basically balance this trade-off a bit. By default, what we use here is v equal to 1 and w equal to 2, which means we give a higher weight to errors. So we try to find a type assignment that ideally doesn't have any errors. Now, given such a feedback function and this combinatorial search problem, you can in principle use any existing search strategy for this kind of problem. So you could formulate this as evolutionary search or any other kind of algorithm. Thinking about these different classes of algorithms that one could use, they're basically two dimensions. One is we can look at, we can take a more optimistic approach, which would mean that we first add the topmost predicted type everywhere in the code, and then get feedback from the type checker, and then remove some types that apparently are wrong because they cause errors. The other way to go would be to take a pessimistic approach, where we just start with the code as it is, and then add one type at a time, pessimistically assuming that that it might introduce a type error, so we are very careful and just add one at a time. The other dimension is whether the algorithm, the search strategy is greedy or non-greedy, where greedy would mean whenever the score decreases, so things get better, we just keep this type and never go back. And non-greedy would mean we sometimes backtrack to avoid getting stuck in a local minimum. Now we've explored this space of different search strategies, and without really going into all the details of how this works, let me just show you this example again and try to illustrate what we do. So let's say we take an optimistic and non-greedy strategy, then we would basically add the first predicted type for each of these type annotations. So int for color, string for the return type of find match, and list for the return type of colors. And then what the type checker would tell us that is that string can't really be the return type of this find match method because it sometimes returns none. And then what we would do is at some point we would remove this type annotation and say, hey, this was wrong, and then try the second most likely as predicted by the model, which in this case would be optional of string. And optional of string is actually the type you want to have, because sometimes this returns a color, which is a string, and sometimes it does return none. So optional of string is just the right type. Cool. So yeah, at this point, let's do another little quiz where again, I've written down a few sentences, some of which are correct and some of which are not correct. And your task again is to tell me which of those you think are actually correct. All right, so yeah, looking at what you're voting, you're partially correct. So most of you think that the second and the fourth sentence are correct, but actually the second one is wrong, and instead the first one is correct. So the first one is that typewriter guarantees to suggest only type correct annotation. So that's a property I haven't really mentioned. So yeah, it was a bit unfair to ask that actually. But so typewriter does provide this guarantee, and the reason is simply that it type checks every assignment of types to type slots, and at the end it only does predict or it only returns to the developer a set of annotations that does not introduce any new type errors, so that is type correct, at least if the code was type correct before. I hadn't mentioned this, so yeah, so I'm not mad at you for not getting that right. The second one is actually wrong. So typewriter does not always suggest the topmost predicted type for each missing type annotation, but instead it has this search, right? So if it sees that so it starts with the topmost predicted one, But then if it sees that this does introduce type errors, it will go down the list and try others until it has found a type correct way to add type annotations. So just predicting the topmost would be an alternative, but it would then probably overwhelm developers with lots of not correct type annotations, and that's exactly what we want to avoid. The third sentence was the size of the type vector equals the number of missing type annotations, and that's wrong, as all of you found out. Instead, the size of this type vector is the number of types that we have in the pool of types that we predict from. And then finally, the last sentence was also correct. So the search avoids the combinatorial explosion of trying all combinations of suggested types by trying to navigate this space of possible type assignments in a more clever way. Cool, so thanks for voting on that. I see some questions that came in the meantime, so let me go through those. So one is, long shot, couldn't the genetic algorithm be used to perform the search? Yes, that is indeed something we could do. So this is a combinatorial search problem. So you can essentially use all these meta-heuristic search algorithms that exist, including genetic search, including A*, including ant colony optimization, or any other kind of search strategy. What we did here is to implement a relatively simple algorithm on our own that has these different variants: optimistic, pessimistic, and greedy and non-greedy, and then we report in the paper which of those works best. Have you thought about applying typewriter to support writing type definition files for JavaScript libraries? So basically a support for TypeScript. That's a great idea. So we did. So this typewriter idea emerged from an earlier piece of work called NL2Type, which was predicting types for JavaScript. And it was only using natural language information and was not using this combination with a gradual type checker, but it exactly emerged from JavaScript, and the types that were suggested by NL2Type can actually be then used as type annotations for JavaScript libraries that will then help to get more type guarantees if you use TypeScript. And of course, this typewriter idea could also be implemented for JavaScript, which is in this specific project have done it for Python. Okay, then there's a question: is the second related to the greedy, ungreedy approach previously mentioned? What do you mean by the second? I'm not sure if I understand that question.
Hi, so the second, I'm referring to the second list that is incorrect in the quiz.
Oh, the second sentence.
Yes.
No, the second sentence is referring to this idea of a search overall. So if you would just take the topmost predicted type, we would not need a search, right? We would just say, hey, these are the types. But what we instead do is we know that for each type slot, there is more than one type that is predicted. And now we search for a combination of types that at the end give us a type correct program. And then now greedy, non-greedy is about how we navigate through the space of these possible combinations. If we take the greedy approach, then whenever our feedback score gets better, we never go back basically. So we only modify other types. So let's say we add, let's say we correctly predicted, let's say we added a type here, and we see that the score gets better. Then in the in the greedy search, we would never go back and never change this type slot again, because after all, we've done something that has decreased the score. But in the non-greedy one, we would sometimes go back and revise this decision maybe.
Okay, perfect. Thanks.
Cool. And then there was a question: how difficult would it be to predict something like this, callable of union of type A of option? Okay, some relatively complex combination of parametric types. It's so the good thing is that well, I'm not sure if it's a good thing, but as a matter of fact, developers do not really write these really complex combinations of parametric types that often. they do to some extent. So you find things like optional of something, you see list of something, you see list of something. It gets a little bit more complex, but it rarely gets as complex as what you show here. And that's why these very complex combinations of parametric types do not end up in our type vocabulary. So they are not in the type vector. And therefore, we don't really suggest them. But then if we would have a code base where developers like to use these types, then, well, they would be part of the type vector, and we would predict them. And yeah. Good. Let me then briefly mention a few bits of the results that we got from typewriters. So one thing we can look at is just the neural model. So basically just the first part of this typewriter approach. And what we see here is results for precision and recall. Precision basically means if you predict a type, how likely is it that this type is correct? And recall means out of all types that we would like to predict, how many do we predict correctly? And the reason why these two are not the same is because the model sometimes says, I don't know. And then this creates this difference between precision and recall. So what we find is that the precision, if you just look at the top one prediction, depending on whether we talk about return types or argument types, and whether it's on the Facebook code or on some open source code, ranges between 58 and 73%. And if we look a little further down the list into the top 5 predictions, then it goes up to 92%. Recall looks roughly similar. So in the top 1, it's between 50 and 60%, and in the top 5, it's a bit higher. Now, this is only the neural model. If you combine it with the search, then the best of the strategies that we have explored adds 72% of type correct types out of all types that we would like to add. And it even completely annotates 44% of all files. So for 44%, we're given a file that does not have all type annotations, and typewriter can fully annotate this file in 44% of the cases, and guarantees that the types that it adds are actually type correct. So yeah, as you see, it's not perfect. It doesn't work for all types. It doesn't work for all files, but it definitely moves the needle by adding a lot of additional types that otherwise nobody really wants to bother adding. This is also why this tool is now used at Facebook. So it's used by developers there, and has already suggested many thousands of types that the developers then have actually incorporated into the code base. All right, so let me summarize this this part of the tutorial. So yeah, I've presented typewriter, which is this combination of a neural type prediction with search-based validation. So in contrast to debugs, which was purely neural, we here also make use of some of the existing analysis techniques that exist, in particular a gradual type checker, and do this in a search-based manner. One interesting feature of typewriter is that it makes use of both natural language and programming language information, and uses this this hierarchical neural network to incorporate all this information into a single prediction. And it has this property of ensuring type correctness. So whenever typewriter tells you that this is the type you should add, that it has already run the gradual type checker. So you as a developer basically just have to say yes, and you know that a type will not break your type correctness. All right, so this is all I have on typewriter. If you have any more questions on that, then now would be a good time to post them. Oh, right, yeah, someone is posting an independent open source reimplementation of the neural model of typewriter at TU Delft. So yeah, while I did a sabbatical at Facebook, Georgios Giousos, who is a professor at TU Delft, was also there with me, and we collaborated on typewriter. And yeah, this is a link to an independent reimplementation.
Georgios.
Sorry, can you say that again?
I worked with Georgios and we re-implemented the typewriter.
Yeah. I know. Yeah, thanks for bringing this up. That's great, because the typewriter implementation unfortunately is not available because yeah, Facebook IP. But there's an implementation, at least of the neural model, that you can use. Cool. Yeah, if you have no more questions on this second example, of an existing learning-based analysis, then let's now move on to the fourth and last part of this tutorial, which is a hands-on exercise. So what we'll do here is that I'll share a link again through the chat. And this link goes to a Jupyter notebook hosted on Google's Collaboratory. So it's basically their cloud-based platform for Jupyter notebooks. And what you'll be able to do there, so you need to log into your Google account in order to modify this notebook. So it's strongly recommended that you do this because you are supposed to play around with this. I'll also go through the code now with you, so you can basically get an introduction, and then at the end we have a couple of exercises that you're invited to do to basically understand this a little bit in more detail. So while you are all clicking on this link and log into Google and then hopefully see what I'll show you also in a few moments, let me just switch to a different window again. All right, so now you should be able to see this collaboratory, so this Jupyter notebook that I've opened here. And what this does is it takes one of these two examples that we've seen, namely debugs, and tries to go through this approach in a small interactive tutorial where you can basically try out things yourself. This is not the full implementation of debugs, but a simplified version of it that looks at only one bug pattern, namely swapped arguments, and that uses less data, and it also has a couple of other simplifications. But I hope it gives you an idea of how this works and also allows you to basically play with this kind of learned program analysis on your own. So if a few of you could basically confirm that you are able to see this and open this, maybe in the chat, that would be great, just for me to know that you are where I think you are. Okay, I see a couple of yeses. Does anyone have a problem accessing the Jupyter notebook? So if you run into some problem, then maybe just let me know now, so maybe we can resolve it, because otherwise it will be a little hard to follow the last part of the tutorial. All right, I don't see anything. So if anyone has problems, let me know. So I'll quickly go through this code and basically explain what it's doing, and then I'll let you work on it and let you ask questions and try to help on demand. But I first go through this just for 5 minutes so you know how this starts. So this is a model that works like debugs for swapped arguments. So for example, it should find out that this call where we call setPoint with yx instead of setPoint with xy is probably wrong. And to do this, I've prepared a small data set for finding these swapped function calls, which you can download by just running this. And then once you've downloaded this, you have the data on your on the virtual image that is attached to this Jupyter notebook and runs somewhere in the cloud. For those who have never used these Jupyter notebooks, I guess many of you probably have, but you can run these individual cells by just clicking this play button here, or you can also run everything by going to runtime run all. I recommend that you go through it step by step so you really understand what's going on. So once this is downloaded, you can unpack it, and then what we see here is that we have lots of JSON files that each contain information about a sequence of calls. And for each call, we have different pieces of information, such as the name of the function that is called, the name of the first argument, the name of the second argument, and some other things that you should explore later on your own. So now what we do here is to have Python code. We first import a couple of things we'll use, something to read JSON, NumPy, a library for handling arrays and multidimensional arrays, basically, and doing computations on them. And then we use Keras, which is one of the popular frameworks for implementing neural networks. Keras is nice in the sense that it gives you a relatively high-level view on neural networks. So as you'll see in a few lines, you can basically implement a neural net. without going really deep into all the details. It's not that great if you want to go into the details. So if you work more in this area, I would recommend using something like PyTorch or maybe TensorFlow. But to get started, Keras is wonderful. And what we do import here is the following. So we import this sequential class, which is basically feed-forward layer, and this dropout class, because you want to implement some dropout, and then dense is just to sorry, I was wrong. So dense is actually a fully connected, densely connected layer, and sequential is just a normal feed-forward model in which things just sequentially move from the input to the output. All right, what we then do here is to just go through the data that we have, that I've provided to you. And when loading all these JSON files, you'll see that you have 28,000 different function calls to learn from. So that's not the multiple millions that Debugs was actually learned on, but it allows you to basically train this model here in the Jupyter notebook in yeah, maybe half a minute or something like this. What I'm also providing to you is a pre-trained embedding of a pre-trained word2vec embedding. Oh, no, I broke this. Let me just fix this. Okay. Which comes in form of another JSON file, and what this JSON file basically contains is a map from a token, something like an identifier or an operator, to a vector of numbers. And if you load this, then you get 9,930 of those embeddings. So basically for the, not all tokens, but for most of the tokens that you have in this code base, you also get a vector representation that yeah, brings similar identifiers close to each other in the vector space. Okay, so now we've loaded all this data. Let's now prepare this data for learning, which basically means we need to go from code snippets to actual vectors. And what we do here is what I've described also earlier in the talk. So we will create these positive and negative examples and then encode each of them as one vector, which we will use as data for training. So let me move directly to the code. So we will fill these two arrays, x's and y's, where the x's are all the inputs and the y's are all the expected outputs. So the first element in this list will be the vector representation of a piece of code, along with the probability that this code is buggy, as we would like the model to predict it. And then we have many of these pairs that are in these two lists, x's and y's. To fill this list, we now go through all the calls, and for each of the calls, we extract three pieces of information. We extract the callee, so the name of the called function, the first argument, and then also the second argument. Then we embed each of these pieces of information, so these three identifier names, into a vector using the pre-trained vector embedding. And then we concatenate those into this vector representation of the entire code snippet, where for the positive example, we just take the vector representation of the called function, the callee, plus the vector representation of the first argument, plus the vector representation of the second argument. And for the negative example, so the buggy one, we just swap the last two things, emulating what would happen if the developer had written the code incorrectly by swapping the arguments. And then here we just add this to our lists, x's and y's, where we add the expected probability 0 for the positive example and 1 for the negative example. Then moving on, we split the data into training and validation data. So 90% is used for training, the rest for validation. And what you see then is that we have, yeah, some number of these examples. It's not as much as you would like to have, but it's enough to get the idea and get a more or less okay model. Okay, so now we have the model. Now we have the data as vectors. So let's now train this model. And what we do here is we just build up this model using Keras. And as I said, Keras is great in the sense that it allows you to build a model in just a few lines of code. So what we do here is we say, okay, we want to have a sequential, so a feed-forward model we want to use a little bit of dropout on the input. So basically sometimes forget some of the neurons that are in the input vector. Then we have a fully connected layer of size 200 with some activation function. And again, a little bit of dropout also in this layer. And finally, another fully connected layer, which then at the end gives us an output vector of size 1. And this is the probability that this code is buggy. Then what we do here is to compile the model, which basically means we provide this architecture that we've built to Keras, also say what the loss function here is and some other details which you can ignore for now. And then this fit call is actually training the model. And here we say how large the batch size is. So basically in what samples we would like to go through all the training data and how often we want to do this. So the number of epochs is 5, which means we go 5 times through all the training data. And then if you run this code, what you see here is how well the model works after the first epoch, the second epoch, and so on. And then at the end, it shows you the training accuracy. So basically how well it works on the training data, which in this case is 89% or almost 90%. So not too bad, given that this is a very simple model with not that much data. Of course, the accuracy on the training data is not that interesting because maybe the model overfits horribly and doesn't really generalize to other data. So what you really care about is the validation accuracy, which we compute here. So now we take this trained model and feed in all the positive and negative examples that we have not used for training, and then see how well it works on this data. And here it's 84%. So not quite as good as on the training data, but still reasonably okay. All right, and then once we have trained this model, we can actually do, we can put it to use and use it to check some code for bugs. So the way I do this here is I'm cheating a bit, so I'm not parsing the code really, because this would involve a bit more code, which you don't really need here. But let's assume we have a call that looks like this: set timeout with delay and fn as the second argument. So this happens to be one of the bugs that I've shown you earlier. Then what you could extract from this function call using some AST manipulation library, for example, is the fact that the callee is called set timeout. And we're using this prefix ID to just indicate that this is an identifier. That's a technicality that you basically can ignore for now. And we also extract the name of the first and second argument, so delay and fn. And then again, we represent all of this in the same way as a vector as we've done during training. Put this into a list of x's, which now has just one element here, and then give this to the model and see what the model predicts. And what it predicts us is the probability that this looks buggy. And indeed, it tells us that, hey, this looks buggy with 99% confidence. So it's a pretty strong indication that this is indeed buggy. And this is also what we had hoped this model to achieve. All right, so now if you have understood everything I said, and probably you want to go through this yourself and maybe play a bit with some of the code, then I also have a couple of exercises down here that basically ask you to modify the code a little bit or answer one of these questions. So I'll basically ask you to go through this yourself and write down these answers somewhere, and then at some point, maybe, I don't know, in 20 minutes or so, I'll give you some answers here. In the meantime, what I suggest is that whoever has any problems or wants to ask anything, just ping me in the chat, and then I'll try to answer these questions either in the chat or through voice, depending on what exactly the question is. Oh yeah, maybe to give me okay, that's a question. That's great. So to give me an indication when you think you are ready. So basically, if you know the answer to all of these questions, then please write it in the chat so that I get an idea just how far you are. Okay, so someone got a different validation accuracy and a different bug probability. That's possible. So all of this training is non-deterministic. It, for example, depends on how exactly the neural network is initialized. So what are the weights that are used at the beginning, and depending on what exactly these weights are, the training will go in slightly different directions. Overall, the overall result should stay more or less the same, but you will see some differences in the accuracies and probabilities. Yeah, so some of you made an interesting observation and reported that in the chat, that increasing the number of epochs increases the training accuracy, but does not really improve the validation accuracy a lot. So what you see happening here is that the model overfits. So at some point, the model will become better and better on the training data, but not because it generally understands how these bugs look like, but just because it gets better at identifying the different names and examples that it sees during training. And typically what people want to optimize is the validation accuracy. So that's why it's usually a good idea to at some point stop training to not just overfit to the training data.
Sorry, can I share my answers here or get?
Yeah, go ahead, sure. I mean, there's no test at the end, so. Yeah, so someone is asking or wondering a bit why the values vary so much between different students. So basically, why is the accuracy higher or lower for some of you? Yeah, as I said, it really depends on how the network is initialized, and the effect of this initialization will become less strong if you have more data. So what you see here is kind of an extreme case because there is not that much data that is used. So if you would train on the full data set of debugs, which is also publicly available, then you will see way less variation. I mean, you still may get 0.5% more or less, but it typically stays in that range and does not really vary as much as what you can observe here. Yeah, so deep learning networks are indeed non-deterministic, yeah. Someone else is asking for, well, basically printed this embedding vector of a given identifier and now asks, hey, what does it mean? So it does mean something, but it's nothing that is meaningful to you essentially, and also not to me, because I mean, this embedding vector basically puts this identifier, in your case, the dollar, into a point in the space that this embedding describes. But now understanding this point on its own doesn't really make sense. So what you can do though is to print the embedding vectors of many of these, or let's say 20 of examples like this, and then visualize how close to each other these points are in the space. So I mean, one 2D visualization I have already shown in the talk. There's also a nice tool that is part of TensorBoard. So there's TensorBoard has an embedding visualization tool, which is basically a little web app where you upload a vector of well, many vectors of these numbers and the string or identifier in this case they correspond to, and then it shows you which identifiers are close to each other in the space, and that allows you to understand how good such an embedding really is. All right, yeah, so I'm seeing that many of you are asking good questions and making good observations, and it seems you're playing around with the model. That's exactly what you're supposed to do. That's good. So since it's already 12, let me just quickly go through the few questions that I had here and give you some idea of what I expected as an answer. Of course, many of those answers were already given in the chat, so this is just to summarize. And then I'll just very briefly talk about a few open challenges in this area, and then we're basically done. Or if you have more questions, I'll be happy to, of course, answer more questions. So the first question I had asked you here to do is to look more at this provided JSON data and maybe see what other kinds of properties about function calls there are in addition to the name of the called function, the name of the arguments. And as one of you has pointed out, there is, for example, type information, which is another piece of information we are using in debugs. There's also information about the code location. I think the code location is not that useful for bug prediction. This is mostly for reporting so that you can more efficiently report back to a developer at what line in what file debugs believes to have a bug. The reason why I provided more data in these JSON files is just to make you aware that there is, of course, more data available about this code, and by adding more data, so not just more data points, but other kinds of contextual information, you can often get better results. Then the second question was, how long is the vector that embeds a single token? As some of you have found out, it's 200, and you can basically just look at the length of the vectors that you get from this emp. What is it? From the embedding. Oh, sorry, from token to vector. That's how I call it. If you just look at the length of one of these vectors, you see it's 200, and that's the length of the vector in which all of these tokens are embedded. Then I asked you to play around with the number of epochs and maybe some other hyperparameters just to see if the training gets better. I see many of you have done this, and we already talked about it. And then kind of to see what the effect of different inputs is, I had asked you to fix this bug by basically just swapping this with that, and then run this last piece of code again, and then you should get, and many of you got that, a probability that is very small, maybe 1% or 2%. So the model basically tells you, yes, if you swap these arguments, then it looks more natural, and it's likely to be correct. Cool. So there were some other questions. All right. So one question, is about the embeddings. That's an interesting question. So can we create embeddings independently from the problem to solve? We do here. So yes, you can. The question is this really the best way to do it? It depends, right? So there is related work that, so the other option is basically to learn the embedding together jointly with the overall task. In this case, we would basically give some other vector representation, not a learned embedding, for example, a random embedding initially into the model, and then have an embedding layer that just transforms this random embedding into maybe a better embedding, and then train all of this jointly with the entire model. That also works well. One advantage of using a pre-trained model is that you can basically reuse the amazing efforts that other people have spent into tuning and engineering these embedding learning techniques. And all you have to do is provide a lot of code as a token sequence, and then you get a relatively good embedding. So based on all the results I've seen in different papers, it seems a pre-trained embedding is at least not worse than training and embedding jointly with the rest of the model. Cool. So do you have any other questions on the hands-on task? Maybe just wait for 1 or 2 more moments. All right, so if that's not the case, then let me just move to my final slide for today, so which is about some open challenges in this area. So what I've presented to you is this vision of addressing many software development problems using a learned analysis. And well, I think we're at the beginning of this journey, right? So there are some promising approaches that work well, but there are many things to do. So if you're looking for an interesting PhD topic, I think there are plenty of things that one could do here. And just to give you a few directions, without going into a lot of detail, I've listed 4 possible directions here. So one is this question of how to actually represent the code, right? So what we've seen here is 2 ways of doing this. One is just this concatenation of pre-trained embeddings. The other one was this hierarchical neural network that uses recurrent neural nets and other submodels to represent natural language and programming language information. These are 2 options, but there's definitely space for more. And there is some other related work that uses other representations. For example, based on abstract syntax trees or more complex graphs that also encode data flow and control flow relations. But there still is a lot of space for innovation here. And I think taking good intermediate representations from compilers, or maybe creating intermediate representations that are well suited for learning, and finding ways of feeding this into a suitable neural network architecture is an interesting direction. Then the second direction is this idea of having better models to reason about programs. So all the approaches that I've shown you today use pretty standard models that are well known in the deep learning area and that have been used successfully in other areas, in particular natural language processing. But now code is not really the same as natural language. There are many properties that code has that natural language does not have. So it makes sense to build models just for code. And some people have started to do this, but again, there's still a lot of space for new ideas here. Then another interesting direction, and some of you have already asked about this, is that it would be cool if you could help developers understanding the predictions that the models are making. Eventually you want to show these predictions to a human, and humans like hints much more if there's some explanation that comes along with them. How to do this for code is still a pretty open problem. So in the case of debugs, I think the problem is less critical simply because it gives you a relatively precise indication of where something is wrong and why the model believes it's wrong, or at least what kind of bug the reason for being wrong is. But for many other models, it's much harder to understand what the model is doing. And typewriter is one example where it predicts some types, but you don't really know why. Right? So yeah, so that's an interesting direction also for future work. And then of course there's this whole space of possible other applications. So right now the community is focusing on a relatively small set of tasks. It's bug detection, type prediction, predicting names of functions, finding clones, and yeah, a couple of others. But it's basically I can 2 hands are enough to list them. I think there are many other applications that these deep learning models on code can be good for, and there are also applications that go beyond just static code, but look at other kinds of artifacts, including runtime traces, documentation, maybe some evidence of crashes, and there's still relatively little or sometimes even no work in looking into these other kinds of data and other kinds of tasks that developers could benefit from if there was a suitable learning-based approach. All right, so that's all I have for today. So I think I can take a few more questions if you want, and then essentially when you run out of questions, we're at the end. And then, yeah, I would hand back to the other Michael. But okay, there's one more question that came in. How many recommendations are accepted by the user? For example, at which position does the correct type have to appear that developers find the tool useful? And what's my experience with that question? So I have some experience with typewriter, and one interesting observation is that beyond the question how precise the tool is, it also matters quite a bit when you show these recommendations. So the best way of delivering typewriters predictions at Facebook that we found so far was to not just have some kind of standalone tool that a developer could actively use, but to integrate these predictions into the code reviewing process. So essentially what happens is if someone changes a piece of code and then wants to commit this change to the main, to the master branch in the repository, then this change goes through code review. So someone else looks at the code, typically in some web interface. And if at this point in time, there is a one-click option to basically just add a few types to this piece of code, then developers are much more likely to do this because then they are anyway thinking about this piece of code, and then just adding a few types is little effort. Whereas if you have a standalone tool and basically assume that people at some point wake up and say, okay, this morning I'm just adding types, then you can wait very long, but this doesn't happen very often because there are always more urgent things to do. So it's not just about the precision, but also about how it's delivered. Now about the precision, I don't really have a lot of data points. I know that for bug finding that is not learning based, at Google, they have this informal 90% rule. So basically the true positive rate should be 90%. Otherwise, a tool is considered to be likely not useful. So yeah, so we are still a little bit away from that number, but yeah. Time for more research, basically.
Thanks.
Yeah, you're welcome. All right, so there's another question. What do you think about training on buggy code from the wild, for instance, from bug issues, bug fix commits from large open source projects on GitHub? I think that's a very valuable idea because it would allow a debugs-like approach to apply to way more bug patterns. Right now, we have this small set of bug patterns. So in a sense, we are still limited by the bug patterns as much as traditional bug detectors are. With the only benefit that here you do not really have to have domain knowledge about how to find these bugs. You just need to have a way of creating these examples. So it's a little better than the traditional approaches, but still it's bound to specific patterns. Whereas if you would actually learn the bug patterns or maybe find the buggy examples from the wild, I think this could be a very nice future work step. Yeah. Good. So it seems.
Okay, seems all questions are answered.
Yep, that's good.
Yeah, great. So Michael, thank you again very much for this great tutorial. And I think the amount of questions really showed that also the participants appreciated it a lot.
Thanks for having me. It was a pleasure to give that tutorial.
Great. Yeah, overall, I really enjoyed your tutorial, but also the other days. I think the online format went very well. I mean, we had 4 amazing tutorials on Safe AI for in the automotive domain, then on software testing for deep learning applications, then on performance engineering for microservice and serverless applications, and finally today on deep learning for software analysis, and also PhD topic presentation and feedback session, as well as an interactive hackathon. Yeah, we will be back next year again, and next year we hope we can do the summer school in a hybrid mode, so also giving you the chance to come to our region, but also to participate online. And in order to do so, we really look forward also to your feedback. Barbara has sent you a questionnaire, and I also post the link to the questionnaire again in the chat. So please participate and help us to make a great summer school also next year. And in addition, it would also be great to get your visual feedback. So please turn on your cam if possible for just a few seconds so that we can see your feedback visually. So all that can, please turn it on at the same time that we can make a nice screenshot. And as soon as I say, then please give us your visual feedback. Okay, so a few more to come, or seems we are in the meanwhile, I can also say those that need a certificate should get it from Barbara. I mean, she prepared for all of you a certificate and they'll send it out. In case there are some issues, please contact Barbara Russo directly. And yeah, I think we will not get many more. So please give us your feedback on the summer school. Great. Okay, thanks a lot. Yeah, and if there are no other comments or someone else from the organizing team wants to make an additional comment, then we close the summer school and wish all of you a great summer, great success with your thesis, and we hope to have some of you back next year as well for the summer school again. Okay, have a nice weekend. And thank you, Michael, again.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
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 Bye-bye.
Yeah, so as people are leaving, I'll turn it off now, right? Okay. Can't hear you, but it sounds like you are nodding, so.